concluded that we have a few breaks in between for questions.
Yeah, I mean, I think you should just pause and indicate during the course of your talk, maybe split it up into 3 segments or something like that.
Yes.
Pause and indicate when you are ready to take questions. And their questions will be in the chat, and I will typically read them out. So.
Okay, very good.
Okay, and yeah, I will use maybe some discretion as to figure out which one to pose and which one not to, if there are too many.
Yeah.
Okay.
Yeah. Good. Excellent.
Fine. I think we wait a few minutes, Sourav.
Yeah, maybe. Maybe another minute or so, and then we can start.
Yeah.
And yeah, people are still joining. So
yeah, people are joining. I mean, it is.
The participants are really from all over the country.
Yes, I think so.
Yes.
Yeah, we have few international participants. But mostly all over the country, and maybe something like 10 people from outside the country.
Yeah.
So one thing which I
sorry, carry on. No, Sourav, you are the organizer. You can speak.
No, one thing which I should have probably stressed is that it is live cast on YouTube. So in principle anybody can join and see. So that's the thing. So. Yes, Sadiq, you were saying something.
No, I was just saying that one of the things is that the venue normally gives an opportunity for a fewer number than what are right now possible because of the online format. Actually, online format works a bit better for India because, we do not have enough opportunities for students and even early postdocs and even early faculty to travel as much. Yeah. So it is, it's actually, it's really a win-win here. In some sense, because many more people can get this exposure.
Yes. Yeah. Yeah, that is true.
So maybe I start my introduction.
Yes, please go ahead.
Okay. So welcome everyone to the morning, afternoon, evening, midnight session, wherever you are in the world, of the ICTS meeting on trapped atoms, molecules, and ions. It is my privilege to introduce Professor Stefan Willitsch. He is at the University of Basel in Switzerland, and so Stefan, I know from a very long time, and there are some very unique things about the kind of physics which Stefan does. But before I get to that, let me just tell you that he did his PhD from ETH Zurich with Friedrich Merz, and followed by a postdoc with Tim Softly at Oxford. And then he was a lecturer at University College London, followed by his position at University of Basel, where he continues to this day. So Stefan, what is unique about Stefan is that he has taken the business of ion trap to a domain where few even today will want to go, which is in the regime of reactions. And he is a chemist, and he brings the solid, he really is a little bit stands apart from a lot of people who come in with atomic physics and then do ion trapping. He is more than ready and happy to explore with molecules and do reactions which most people will not really dream about. He works with trapped iron crystals, and that is his crucible, I would say, and builds up experiments around that, both beam and hybrid trap experiments. And with that, I think I will hand it to Stefan.
Okay, thank you very much, Sadiq, for this very kind introduction. It's a pleasure and a delight to be here with you today, at least virtually, and participate in this school. I'd like to thank give a big thanks to the organizers for this opportunity. And I'm very excited about this program that you have put together. I think this is, in spite of all the mayhem that we are experiencing all around us at the moment, this is a really fantastic thing to organize. So thank you very much. So I was asked to talk about molecules and ions and ion atoms, and I will do exactly that, right? I take the best synthesis of all of these words and talk about cold molecular ions and traps, methods, and applications. And so before I start, let me maybe say a few words about where I come from. So our institute is based in Basel in Switzerland. Basel is a nice medieval town at the fringes of Switzerland, I should say, right at the border between France and Germany. Yeah, as I've said, it's a medieval town core. It's right at the River Rhine. What you see here in my background is the historic building of the university right at the riverfront. So if you ever come to Switzerland, is a place well worth visiting. And yeah, if you have time, then stop by our institute as well. Okay, so what I will be talking about today is cold molecular ions and traps, and their applications in both physics and chemistry. As Sadik has already hinted, I'm a chemist by training, but not only, I'm also a physicist by training. So I've had this ambivalency all my life. And I will, yeah, also in my talk explore this interface area between physics and chemistry and see what one can do with cold molecular ions in both of these areas. So why are cold molecular ions and traps interesting at all? And this is a field that has started to emerge some 20 years ago and has been growing ever since. And there are a couple of I would say, very exciting applications that one can do with this technology, and that all build on the unique properties of these cold molecular ions and traps. And yeah, I mean, one big advantage of this technique is that one can address single particles in the trap and exert a control on the quantum level over them. And that allows one to do quantum logic experiments and develop quantum technologies for these trapped molecular ions. And that is particularly interesting in the framework of precision spectroscopic measurements. But then they also offer opportunities to study interactions between ions and neutrals, yeah, both molecules and atoms, in a new physical regime at very low temperatures. So one can study collisions and even chemical reactions. And what the past years have shown is that one can study some rather exotic chemical processes in this regime, that the quantum character of collisions becomes important. And one important aspect that I will also be dwelling in my lectures on is that this environment and these methods offer quite nice ways to probe fine details of intermolecular interactions that otherwise would remain obscured. And then finally, they also offer opportunities to study and indeed control chemical processes also of very large or of larger molecules, right, in ways that have not been possible before. And that means one can control the quantum state of the molecules, one can control the collision energies, and therefore one can also establish ways to control the outcome of collisions and chemical reactions. Okay, so in my lectures, I will mostly dwell on the first two topics here. And my lecture is split into two parts, one today, the other one on Thursday. Today, I will talk about basic techniques, experimental techniques relating to cold molecular ions and their applications in spectroscopy. And on Thursday, I will talk about cold ion neutral interactions. And so the program for today is I will talk about the cooling and the trapping of molecular ions. You've already heard a lecture on ion trapping by Didi Leibfried yesterday, so which is an excellent preparation for many of the things that I will also be talking about today. I will then really focus on molecules, molecular ions in the traps. I will talk about the internal state preparation, spectroscopy, precision measurements of cold molecular ions, and then I will finish with some new experiments on ion quantum technologies and quantum logic spectroscopy. Okay, so there's a lot of literature in this field already. I've put together a collection of books, which you might want to have a look at if you want to delve more deeply into the subject. And there are many reviews and primary research articles that I will be referring to over the course of my lecture. And you can download the slides from the website of this meeting so that you also have them for yourself later on. Okay, so let's start and begin with a few words on the cooling and the trapping of molecular ions. And I think the salient basics about ion trapping and cooling of ions in traps have already been explained by Didi Leifried in his lecture yesterday. So I will not dwell too much about that, and I will primarily focus on molecular aspects, as I've said. So, but just to briefly recapitulate, so the salient technique that we use in essentially all of our experiments are Coulomb crystals of ions in traps. And what you see here are some false color fluorescence images of Coulomb crystals of laser-cooled calcium ions in the traps. This is a single ion, it's a string of 6 ions, it's a larger 3-dimensional crystal of a few hundred ions. And so what these are is that they are essentially ordered structures of cold ions in trap, right, which form at very low temperatures under a tight confinement in an ion trap. And what all these Coulomb crystals have in common is a couple of neat features, right? They can be very cold, right? Typically millikelvin, but if you work hard, then down to microkelvins. You can keep them in a trap for very long periods of time, right? Easily hours. And as you can see on these images, right, what you can do is you can really observe single particles, right, and therefore also address and manipulate single particles on the quantum level. And that is very neat features that we capitalize on in all of our experiments. Okay, so just a very few basic words about how these ion traps work. I trust that Didi has already covered this yesterday as well. So we want to trap the ions. And since ions are charged particles, the obvious way to do this is to choose some sort of electric field to do that. Now, there is a catch, right? In electrodynamics, you have the Laplace equation, which essentially states that the Laplace operator acting on the electric potential in charge-free space has to be 0. So that means that essentially that with just static electric fields alone, you will not be able to form a minimum of this potential in 3-dimensional space in which you could confine the ions. So what can you do? So the one solution to this dilemma was the development of radio frequency ion traps, right? Starting with the seminal work of Wolfgang Paul in the 1950s, which were subsequently also awarded the Nobel Prize in the late 80s. So his key idea is to use radio frequency fields to trap the ions. So and in most radio frequency ion traps used today, they are typically linear Paul traps, as they are called today. So they are typically an arrangement of 4 electrodes, cylindrical electrodes, which are arranged in a quadrupolar configuration. And then radio frequency voltages are applied to adjacent rods, always with a phase shift of 180 degrees between adjacent rods. And they create an inhomogeneous time-varying electric field in the center of these electrodes. And they are arranged in a quadrupolar configuration to give a quadrupolar field. And what happens then to the ions is shown in this movie schematically. What you see here is the potential in the XY plane. So the XY plane is the one perpendicular to the trap axis. And if you switch these fields fast enough, that what it creates is a saddle point, a rotating saddle point that dynamically, and the switching dynamically confines the ions in the center. And you see here this little ball, this represents an ion, and the potential switch fast enough so that this ion cannot get up. It's confined dynamically. So that's the principle of a radio frequency ion trap. And so in the XY plane, so perpendicular to the trap axis, one uses these radio frequency fields. confine the ions. Along the axis, one can apply static potentials, which are applied to different segments of these electrodes to confine them also along the longitudinal axis of the trap. So that's the principle of these radio frequency ion traps, and that is also a working Horst technology in our experiment. So one can then solve the equations of motion of such an ion in such a radio frequency trap and then work out the trajectories. There are analytical solutions for that, and such a trajectory is approximately given by an expression like this. So the important thing is that the motion of an ion in such a radio frequency traps in principle separates into two components. One of them is a slow oscillation, a thermal oscillation, if you like, a thermal motion, if you like, of the ion in this trap, which is termed the secular motion. But superimposed on that, we have a fast oscillating component, and that is the so-called micromotion. And this is a motion, this is the motion that is driven by the RF field. So it occurs at the frequency of the RF fields. And this is a unique feature of ions in RF traps, to which we will come back many times over the course of this lecture. Can be a blessing and a curse. Yeah, it's a blessing because it makes this trap works to start with, right? But it's a curse because it's also something you have to deal with in experiments. Okay. From the solutions of the equations of motion of this ion in the trap, the so-called Mathieu equations, you can then define so-called Mathieu parameters A and Q, which are defined as given here. You can see these parameters depend on a bunch of experimental parameters like the voltages that are applied to the trap, the radio frequencies, the mass of the ion, charge of the ions, geometric parameters of the trap. And the significance of these parameters is that only a certain combination of these experimental settings lead to a stable trapping of the ions. And these regions of stable trappings in terms of these A and Q Mathieu parameters are usually cast into stability diagrams like shown here. And when you operate your ion trap, you always have to be sure to operate it with A and Q parameters that lie within one of the stability regions of the trap. Okay, so this is just to say that you can't trap ions all the time, right? But only under specific conditions when the stability criteria are met. Okay, so in order to understand how these radio frequency ion traps work a bit better, what one can do is one can then perform a time average over this micromotion. And then this leads to an effective time-independent pseudopotential. And since one likes to construct these traps in a way that in the end, what one gets is in harmonic confinement, is that under these conditions, one then gets a pseudopotential, which is essentially harmonic in all directions, right? So by construction of these traps. And so essentially we have an harmonic confinement of the ions in this trap. And this is always nice because harmonic motion is something that a physicist can well understand. Good, and also this is something that we will need later on more often. So cooling ions in the trap. So Didi Leibschmidt has yesterday extensively talked about laser cooling of ions in the trap, so I will not reiterate that. Just a few important points for what will come in over the course of this lecture. So all experiments start with laser cooling a suitable atomic ion. And the typical ions that are used in these experiments are alkaline earth ions, because they have a simple energy level structure corresponding to an alkali atom, in which it is usually rather straightforward to implement a closed optical cycle, which is necessary to achieve Doppler laser cooling. And our PET ion is the 40 calcium ion. You see its energy level structure here. So you can implement a Doppler cooling cycle by exciting from the ground state, the 4s doublet as 1/2 state, to the excited 4p doublet p 1/2 state. So you have a laser around 400 nanometers, which you use to drive these transitions, scatter photons on this transition, and then in this way achieve laser cooling. Then we also have the 3D levels. And from the 4p level, an ion can fluoresce down here, spontaneously emit the photon, populate this level with a certain probability. So here, the population would be trapped because going from here back to the ground state is not allowed, at least not in the electric dipole approximation. So one needs another repumper laser to pump the population back in order to close this laser cooling cycle. So this is how typically ion laser cooling works. In this case, in the example of 40 calcium ions, this is also what we use all the time. So maybe another note is that when you laser cool neutral atoms, right, say in a magneto optical trap or so, then you usually have an optical molasses configuration, so 6 counter-propagating laser beams to cool along all 3 directions, and to cool along all spatial directions. If you cool large ion clouds in such a trap, this is usually not necessary because the Coulomb interaction between the ions couples all degrees of freedom. So in these cases, it is often sufficient to just have a single laser beam along one axis of the trap. So it simplifies the experiment a bit. Okay, so that works well for atoms, atomic ions. However, if you would like to laser cool molecular ions, then yeah, you have a problem that molecules are complex beasts with a complex energy level structure, and there are only few molecules in which closed optical cycles can be implemented. And as of today, this hasn't happened in a single molecular ion, at least to the best of my knowledge. So laser cooling, direct laser cooling of molecular ions is therefore not really the way to go forward. But thankfully, there is an alternative technique, and that is sympathetic cooling. And this is highly successful and has become a real working horse in this field and also broadly applicable. And I should point out this specific paper, right, which is now a landmark in the field. I think it's fair to say it's now some 20 years old. And this was the first time when a Coulomb crystal of molecular ions has been produced by sympathetic cooling. And this is now what essentially everyone uses in the field. So how does this work? The idea is very simple. So you have an ion trap, you have laser cooled atomic ions in this ion trap, and then you load molecular ions in the trap. And you keep laser cooling the atomic ions, and by collisions between the molecular ions and the laser cooled atomic ions, kinetic energy is all the time exchanged between them. The coupling between the ions is very strong. It's a Coulomb interaction, so energy is exchanged very efficiently. And this kinetic energy is then in the end transported away by laser cooling on the atomic ions. So what one gets in the end is what is called a molecular or a bicomponent Coulomb crystal. And what you see here is such a false color fluorescence image of a Coulomb crystal of laser-cooled calcium ions, and this is the fluorescence that you see. And in the center of this crystal, intercalated, you have molecular ions, in this case nitrogen ions, which do not fluoresce because they are not laser-cooled, but you can see them in the regions where they displace the calcium ions and are sympathetically cooled and intercalated into the crystal. So what one can do now is one can make simulations of these crystals, and simulations shown here. And in the simulations, one can make these molecular ions also visible, and by a rigorous comparison between experiment and simulations, one can exactly work out how many ions there are and how cold they are. So let me say a few more words about how these simulations work. This has also become quite a widespread tool in the field. Essentially what one does here is a type of molecular dynamic simulation. So one solves the equations of motion of the ion ensemble in the trap under the action of laser cooling and some heating mechanisms. So and the typical force model, which sets up the equations of motion, is shown here. So one has typically a harmonic potential for the trap. This can be the pseudo potential or time-dependent potentials. Then one needs to take into account the Coulomb interaction between all the ions. And then one needs to model the laser cooling and heating mechanisms. And there are different ways how to do this. Different people have found different approaches to that. The easiest thing is just to have a friction force for the laser cooling, and then some stochastic force that effectively takes into account heating mechanisms in the experiment, right? Like electrical noise and what have you. And from such a simulation, and I show you here a movie of such a simulation, this is a cloud of calcium ions, which is under the action of laser cooling in such a trap. And then one gets the trajectories of the ions, and which you can then turn into this movie. And based on these trajectories, you can also then go forward and simulate your Coulomb crystals, right? So this shows simulations of this crystal here. This is an experimental image, and these are simulated images under different secular temperatures of the ions in the trap, and then one can see that the crispness and the sharpness of this image strongly depends on the temperature, and by comparing those you can then figure out that this crystal probably has something like 7 millikelvin secular temperature. And the same also, so already hinted before, right? I mean, you can then simulate, for instance, bicomponent crystals with different number of sympathetically cooled ions. And again, by a careful comparison between the experimental image and the simulated images, by really looking at fine details between the simulations and the experiment, you can then work out that this particular crystal has around 24, maybe plus minus 1 nitrogen ions in the center. And the simulations, they work astonishingly well, and one can really get very good insights into the properties of the Coulomb crystals in that way. Okay, so that is maybe a good point to ask questions if there are any.
So, so far, I think, okay, there is a question. Okay, so let me ask you, do ions radiate electromagnetic waves when it is in the trap?
Sorry, say again?
Does an ion radiate electromagnetic waves when it is in the trap?
Yeah, I mean, a laser cooled ion, for instance, always emits, if a laser cooled, it always emits radiation, right, in that way. But is that what this is about?
I think it's basically about an accelerating ion. It's not very clear from the question, but because...
Yeah, I would think so, yeah.
Yeah, but it's so small that it won't matter in these situations.
Yes, exactly. Yeah, it's a minute effect. Yeah.
Yeah, I think we can go on, Stefan. There are no further questions now in the chat.
Very good. Thank you. Okay, good. So now we have sympathetically cooled the translational motion of the ions in this trap. Now, yeah, let's talk a bit about how we control the internal motion of the ions. Because one feature of this sympathetic cooling is that it only affects the translational motion. So far, I'm not aware of any experiment where one has managed to sympathetically cool the internal motion of molecular ions in that way. And the reason is that the Coulomb interaction, which mediates these collisions and the cooling in the end, is isotropic and acts at long range, and only very, very weakly couples to the internal motion of the ions. And with internal motion, I mean predominantly the rotational motion and the vibrational motion of these molecules. Okay, so what can one do, right? Because I mean, it's not very helpful if you have a translationally cold ensemble of molecules which are internally hot and where the population is just distributed over many different quantum states. And that has been a major problem in the field for, I would say, 10 years in the noughties. And by the end of the noughties, around 2010, people have started to solve it by various means. And one of the first methods was rotational laser cooling, which has been pioneered by the group of Michael Drefsen and also by Stefan Schiller at about the same time. And the idea is that, okay, you start sympathetically cooling your molecular ions to start with, and then you use optical pumping, right, on the Coulomb crystallized molecular ions in order to pump the population in only a few quantum states. And this is an experiment that has been done in Michael Drefsen's group. about 10 years ago on sympathetically cooled magnesium hydride plus ions. What they did is, as I've said, they sympathetically cooled the magnesium hydride plus ions in the usual way. And then they introduced an infrared laser. And this infrared laser was pumping on a specific rho vibrational transition of the ion. So we have MgH plus is a diatomic molecule, so it can vibrate, right? And you see here the vibrational quantum states, vibrational ground state, first excited vibrational state. And then, of course, it can also rotate. And so you have different rotational states, both in the vibrational ground state and the vibrationally excited state. And they were now introducing a laser for rotational cooling, which was addressing a specific rotational vibrational transition, namely from the J-2 level in the ground state. So this is the second excited rotational state. And this was then pumping the molecules to the first excited vibrational state and there in the first excited rotational state. So one quantum of rotation would be taken out of the molecule by this excitation. And from this excited state, the molecule can then emit photons again spontaneously. And by spectroscopic selection rules, it could either only fluoresce back to the J-2 level from where it started or to the J-0 level. Okay, and the aim of this experiment was in the end to put as many molecules into the J-0 level. So if the molecule fluoresces back to the J-0 level, it's fine. Then this is already where we want it to be. If it goes back to the J-2 level, then it can be pumped back. Yeah. So from that perspective, we can pump all the population in J-0. But then in thermal equilibrium, from which we start, we have a distribution of populations. And we not only have population in J-0 and J-2, but also in many other rotational states. So what do we do about them? There's also black body radiation in the experiment. It's a room temperature experiment, and black body radiation can couple the different rotational levels and can pump populations in between those levels. So J-0 would get depleted after time by this pumping, but black body radiation would then pump population from neighboring levels, say J-3 and J-1, into J-2, from where it would eventually be pumped into J-0. Yeah? And so after doing this for a couple of times, right, on the order of a minute or so, the population would then accumulate in J-0 by this combined optical pumping of this additional laser and the black body radiation. And in this particular experiment, they managed to increase the population in J-0 from maybe 4% to about approximately 40%. Yeah, so a factor of 10 increase, which is already a big improvement compared to what we had before in thermal equilibrium. So this is rotational laser cooling. You can further improve this scheme by introducing additional cooling lasers. And for instance, in Stefan Schiller's group, they have managed to prepare, in their case, HD plus ions with a state purity in J-0 on the order of almost 90% or around 90%. Okay, good. So another approach has been developed in our group around the same time, and it followed a completely different philosophy. So our approach was to avoid this whole problem from the very beginning. Yeah, we did not want to start with an internally hot ensemble of ions. So what we tried to do is we tried to produce the molecular ions already to start with in a specific quantum state, and then keep this quantum state as long as possible. So, and in order to avoid having to do any optical pumping on the internal degrees of freedom. So how can one do this? The method that we adopted is called threshold photoionization. And the idea is the following, that you photoionize the molecules, the neutral molecules, to generate a molecular ion inside the ion trap ultimately. And you do this photoionization in a way so that by virtue of selection rules and energetic constraints, which are also always present in the photoionization process, you produce the molecular ions only in a specific quantum state. Okay, so let me become a bit more concrete. So one of our favorite molecules is nitrogen, as you have already noticed, and the nitrogen molecular ion. And one of the big advantages of nitrogen is that it's an apolar molecule. It does not have a dipole moment, and therefore it does not couple to black body radiation. Yeah. Remember, in the previous rotational laser cooling scheme, black body radiation was essential, right, to redistribute population. Here, we want to avoid this, and this is why we choose a molecule which doesn't couple to the black body radiation field, because it's not polar. It doesn't have a dipole moment. Okay, so, and one can then devise a photoionization scheme in nitrogen. So never mind all the spectroscopic notation here. Suffice to say, we take a laser beam from which 2 photons excite neutral nitrogen to an electronically excited state. And in this electronically excited state, we pick a specific rotational level. And then we take a second laser beam to ionize the molecule with 1 photon to populate specific levels in the ground state. And what you can see here is what is called a rotational resolved photoelectron spectrum. Okay, so there's a spectrum that you get out of this photoionization process. And what you see here are different spectra taken out of different rotational states here in this intermediate electronic state. And every line that you see in this spectrum corresponds to the formation of the ion in a specific rotational state. Yeah, for instance, in this one, if we go via the second excited rotational state here in this intermediate state, and if you then ionize the molecule, then because of photoionization selection rules, you can produce the molecular ion either in the rotational ground state, second excited rotational state, or the fourth excited rotational state. Now suppose you do just that, you ionize via this specific intermediate level, and then you choose the ionization frequency, or the frequency of the ionization laser below this first band here, right? So this is essentially, this is the ionization threshold of the molecule. And if your ionization energy is below the if your laser energy is below the ionization energy of the molecule, of course, you are not producing any molecular ions, right? And so essentially nothing happens. Yeah, we only, in the experiment, we only then have a Coulomb crystal of laser-cooled calcium ions, no molecular ions. And if we then slightly increase the laser frequency to go above the lowest ionization threshold, and this is the threshold which corresponds to producing molecular ions only in the rotational ground state. Say if we park the laser frequency here, then we start molecular ions, producing molecular ions, and for energetic reasons, we can only produce them in the rotational ground state. And then we sympathetically cool them, and in this case, we produce the molecular ions, and they are then all sympathetically cooled into the Coulomb crystal. That is essentially the image that I already showed you before. These molecular ions that have all been produced in the rotational ground state and then sympathetically cooled. So in this way, one gets in theory state pure molecular ions, which are also translationally cold. So they are all in the vibrational ground state, they are all in the rotational ground state. And as a matter of fact, this was actually the easy part of the experiment. The hard part of the experiment was to prove that this really works, right? In order to prove this, you have to do molecular spectroscopy on these ions to read out the populations in the different rotational states. And that actually turned out to be the hard part of this experiment. Because in here, as I've already said, we have around 24, 25 molecular ions. So one needs a very sensitive spectroscopic technique to detect spectroscopic excitation in such a small ensemble, right? I mean, this is really homeopathic, if you like, right? We only have, 20 to 30 ions here on which we want to do spectroscopy. So what can one do, right? And at this point, it actually helps if one also knows a bit about chemistry, because these chemists, they tend to have a couple of tricks up their sleeve. And one of them is one can use actually chemical reactions to detect the spectroscopic excitation. And that is called action spectroscopy, because one detects the spectroscopic excitation by a specific action. And in this case, in our specific case, what one can do is it has actually been known for quite some time that N2 plus ions, nitrogen ions, can undergo a charge exchange reaction with argon atoms. So an electron hops over from argon to N2 plus, and one gets neutral nitrogen and argon plus. But this only works if the nitrogen ions are vibrationally excited. And the reason is there is a small mismatch in the ionization energies between nitrogen and argon. and one needs some extra energy in the vibration of the nitrogen to make this process energetically possible. If the nitrogen ions are in the vibrational ground state, this doesn't work. Yeah, and now you can use this to detect the spectroscopic transition very sensitively. So we use this to map out the rotational state populations of our state selectively produced ions in the following way. So we took another laser beam and then we excited these state selectively prepared molecular ions out of different rotational states to an electronically excited state. And from there, eventually it would fluoresce back to the electronic ground state of the molecule, populating vibrationally excited states in this fluorescence with a probability of 55%. 45% would go back to the vibrational ground state, but 55% would go to vibrationally excited states. And and those we can detect then with the charge transfer scheme, right? Because those will then undergo charge transfer with argon. The nitrogen ions will disappear from, they will be neutralized, they will disappear from the Coulomb crystal. And this is something we can see in the images. And that is shown here, right? So these are nitrogen ions in the crystal before this laser-induced charge transfer scheme, as it is called, and here afterwards, right? After this excitation and fluorescence back to vibrationally excited state. And again, using simulations, one can analyze this. Initially, we have 24 ions. Afterwards, we have 12 nitrogen ions left. So 50% have gone away, meaning 50% have ended up in vibrationally excited states when they were pumped out of here. And so this is 50% is very close to this 55%, which is theoretically possible. So if one does a bit of statistic now, then one realizes that about 93% of the ions were in the rotational ground state, and not in rotational excited states. Okay, so this is a way to do spectroscopy on the ions, and at the same time prove that the state selective generation of the ions really works. Okay, so I should also say that, I mean, these were the very first experiments that have been done to state selectively produce ions. Time has gone on, and a range of other techniques have also been developed to address this problem. For instance, there have been some very beautiful experiments, again, from Michael Drefsen's group, where a combination of sympathetic cooling and helium buffer gas cooling, so cryogenic helium buffer gas, was then used to cool the internal degrees of freedom by collisions. Then there was also a variation of rotational laser cooling using broadband excitation with femtosecond lasers implemented by Brian Odom's group. We have also buffer gas cooling of molecular ions by ultracold atoms. This has been demonstrated by Eric Hudson's group. And there are also ways for probabilistic state preparations of ions, right? So projecting ions into a specific quantum state by just measuring this quantum state. And this has originally been proposed by Michael Drefsen in this paper here, and this has been implemented in our own laboratory, or a fashion of it has been implemented in our own laboratory very recently. So this is all the techniques that are essentially available at this particular moment. So that is another good point to ask questions, if there are any.
Yes, there are a few questions, so I will take them one by one. So the first of these is, how do you detect the rotational state population and verify if optical pumping schemes work?
That's a very good point. So I will actually talk about this in the next part of my lecture, how they did it. They also did a type of spectroscopy, but a different flavor of spectroscopy compared to what I have shown you for our experiments. But I will come back to that in a few minutes.
Right. So then let's move to the next one. One of the methods you mentioned for measuring the temperature of the iron crystal is to compare your experimental result image with the simulation image. Mm-hmm. This is somewhat like an indirect method. Can we use radio frequency excitation to get an idea of the secular frequency and hence the temperature. What are the other direct methods?
So yes, you can also use excitation methods, right? Coupled with ion ejection methods in many cases to get an idea about the temperature, right? I mean, I think Sadik, especially yourself, you have used these sort of techniques many times to get an idea about ion temperatures. There are other direct methods, which I partly will discuss over the course of my lecture. You can do, if you are in the resolved sideband regime, you can do things like Rabi thermometry. You can also do a recooling type of spectroscopy, right? If the ions are hot, right? And then you can just track the time for how long it takes until they cool again. And this gives you also some ideas about the initial temperature. So there are various ways, yeah. The simulations are very nice for big ion crystals. They don't work well for small ion crystals, and for small ion crystals, one would use other techniques like sideband thermometry, which I will also discuss very shortly, and which I think have also already been introduced by Didi Leifrid yesterday.
Right. So let's move to the next question then. In the detection scheme for rotational cooling, do you use the single atom readout of the 25 N2 plus ions?
In these particular experiments that I have shown, not, yeah, but in later experiments, which I will discuss also shortly, we do that. We do exactly that. Yeah, we do a single atom readout.
One more question. Why does the second image after laser-induced charge transfer look a bit squashed?
So this is an excellent question. So I presume it refers to, let me see, this one here. Yeah. So indeed it is asymmetric. Yeah. And the reason is that we have radiation pressure coming from the right-hand side here, which pushes the laser-cooled calcium ions, which fill up these holes to the left-hand side. Okay, and I see with squashed, you probably mean that the crystal looks a bit like eaten away. Yeah, very good. This is a very perceptive remark. So what is happening here is also that in our experiment, so this takes several minutes, right? And the pressure is about 10 to the minus 10 millibar, but we still have a bit of hydrogen left in the background vacuum. And this hydrogen reacts with the calcium ions to give calcium hydride. And these calcium hydride ions are then sympathetically cooled at the outskirts of the Coulomb crystal. And this is what causes this squashing here. So very good question. Thank you.
Yeah, I think that kind of sums up this round.
Okay, very good. Then let's move on with the next part of the lecture. So all these techniques that I have been talking about so far, they can now be used for useful things, right? And one useful thing is, for instance, spectroscopy. And there are many different techniques in ion spectroscopy around that have been developed for decades, right? So why do such a complicated experiment as we and others are doing now? And the answer to that is that the advantage of these cold and controlled ions is that there are prospects to do spectroscopic experiments very precisely. So it's about precision spectroscopy. And why is precision spectroscopy interesting? Well, there are different applications that you can think of, right? You can use a very precise spectroscopic measurement in a specific system to come up with new types of clocks, right? So instead of atomic clocks, you can think of atomic ion or molecular ion clocks. And this is also actively pursued these days. Very precise spectroscopic measurements can test the validity of our basic physical theories like quantum mechanics or quantum electrodynamics to an exquisite degree of precision. One can test, fundamental ideas that are around. For instance, is there maybe a time variation of fundamental physical constants? For instance, the electron to proton mass ratio, yeah, molecular spectra very sensitively depend on this number here. And in case these constants vary with time, right, it should be reflected in molecular spectra, which one then could measure or should measure very precisely. There are also ideas, or not only ideas, but also real experiments which use precision molecular spectroscopy to search for new physics. For instance, to determine the size or the magnitude of the dipole moment of the electron, right? And this then ties into the question of post-standard model theories. There are also questions, are there fifth forces and manifest themselves in molecular spectra? Are there maybe extra dimensions which could also influence molecular spectra? So these are questions that are being asked. And also in a question of more relevance to molecular physics, maybe if you think of more complex molecules, then you have often molecules that appear in two different forms, image and mirror image. And then the question is there a slight energy difference between them, right? And it has been, and nature has chosen one specific form of these molecules, for instance, of all the amino acids and sugars, only a specific form is used and not the other. And the question is why is that so? There seems to be some interference now. Yeah. So.
Hello, can everyone switch off their mics, please, except for Stefan?
Okay, now it seems to be good. Thank you. Okay, so these are all motivations why one would like to pursue extremely precise spectroscopic measurements on molecules. Yeah, so how to do this, right? One needs to do spectroscopic measurements on cold molecular ions. I've already introduced one method, laser-induced charge transfer, or more generally, laser-induced reactions that can be used to detect spectroscopic transitions. Another possibility is photodissociation spectroscopy. And that has been used by many other groups in a range of other systems, MGH+, which I've already talked about. So here the populations were read out with photodissociation spectroscopy, or notably also HD+, where this has been used with great success. And this is an experiment from Stefan Schiller's group, where they are particularly interested in precision measurements of HD+ ions. It's a fundamental molecular ions, one of the simplest there is, right? Hydrogen molecular ions. So what one can do in these cases is they are interested in infrared spectroscopy. And so they take a first laser to excite the vibrational overtone in this molecule with an infrared laser, and then take another laser in the UV to photodissociate the molecular ion once it has been excited to this excited vibrational state with another photon, and then they detect this photodissociation event. Okay, because then the molecule is destroyed, and this changes the composition of the Coulomb crystal. And specifically, in these experiments done here, what they did is the following. They used beryllium ions to sympathetically cool HD+ ions. I should mention that in order to get efficient sympathetic cooling, the masses of the coolant, here beryllium, and the ion to be cooled here, HD+, should be roughly similar. They shouldn't differ too much. So this is why beryllium was chosen to sympathetically cool HD+. And so this is again a bicomponent Coulomb crystal. It also already contains a bit of B+ in here as an impurity. And in order to determine the composition of this crystal, what has been adopted is a type of resonant excitation mass spectrometry. So the different ion species in the trap, they have different motional frequencies, because the oscillation frequency of an ion in the trap depends on its mass. So in principle, they oscillate with different frequencies. And one can then apply an additional oscillating electric field to the trap electrodes and resonantly excite the ion motion for different species, which differ by their mass. And this excitation then couples heat into the crystal, and the heat, and this then changes the fluorescence of the crystal, as we have already seen before. And so in this way, this is a way to do mass spectrometry actually on such a crystal and figure out what sort of ion species are in this crystal. And of course, if in the course of this photodissociation spectroscopy, Hd plus ions are photodissociated, giving D plus ions, and this then shows such a resonant excitation experiment where continuously the ions were excited here and then photodissociated. And one can see the Hd plus signal, which is this peak here, which diminishes as a function of time. And instead, another signal comes up. This is this D plus signal here from the D plus ions that are generated in this photodissociation. So this is a blow up here of this curve here. So in this way, this photodissociation event can be detected, right? And again, the photodissociation happens if the molecular ions have been excited beforehand by this infrared laser. And that is again a detection scheme which you can then use for spectroscopy with this infrared laser. This is shown here. This then shows a specific rotational vibrational transition in Hd plus. It's broadened by hyperfine structure. There's hyperfine structure lying underneath that. And but in this way, it is possible to map out these spectroscopic transitions. So these sort of schemes have been refined over the years. And this is a very recent experiment from the group of Jérôme Colomé in Amsterdam, also on Hd plus, where they have done Doppler-free two-photon spectroscopy. Yeah, so I should say that the line with here is to a large extent caused by, well, the unresolved hyperfine structure, but then also by Doppler broadening, right, at the residual temperature of these ions in the trap. So what one can do in order to eliminate the Doppler broadening is using a two-photon spectroscopy, yeah, two laser beams with a very similar wavelength that are introduced into the experiment in a counter-propagating fashion. Yeah, so in this way, the Doppler shifts cancel, and one eliminates the Doppler shift from the entire spectroscopic problem. So they had two laser beams. First one was exciting from V equals 0 to V equals 4, and then the second one from V equals 4 to V equals 9. Wavelengths have to be similar to get this Doppler cancellation condition. And then from V equals 9, they would then photodissociate and then detect the spectroscopic excitation again by this photodissociation scheme. Now, there is hyperfine structure underneath there, as I've already said. I don't want to go into all these gory spectroscopic details. Suffice to say that there is a forest of lines underneath. And with this Doppler-free scheme, they could then really resolve different hyperfine components, right? So mind you here, this is a kilohertz scale now. And before here, we had a megahertz scale, right? And all these lines which were unresolved can now with such a Doppler-free scheme be resolved. Yeah, so it's a very nice experiment. And what they then did with this technique is that they used this in order to determine the value of the proton to electron mass ratio very precisely. Yeah, so not the time variation, but the value, the actual value of this ratio. And they compared this then to previous determinations. And to my knowledge, this is so far the most precise determination of this ratio. So this is a very nice application of this technique. So, I mean, this then begs the question, I mean, in the end, it's a quest for reaching ever more precise spectroscopic precision. And this now starts to raise the question, okay, so what sort of spectroscopic lines in a molecule should one pick for these sort of experiments? Yeah, ultimately, one needs to measure them very precisely. So these lines need to be very narrow. And so that poses some quite stringent restrictions on lines that one can use. Because the width of a spectroscopic line is in its last consequence determined by its natural line width, yeah, meaning the lifetime of the excited state of this transition. And if this transition is dipole allowed, so if it is allowed within the electric dipole approximation of the coupling of matter with radiation, then it's usually reasonably strong, and consequently its line width is rather broad. And one of the reasons why HD plus was chosen is that I mean the dipole, vibrational transitions that are addressed here, they are still allowed within the electric dipole approximation, but they are very weak because this molecule only has a very weak dipole moment. Yeah, because I mean it's isotopically polar, if you like. Otherwise, it would be an apolar molecule if it were H2 plus. And in these homonuclear diatomic molecules like H2 plus, or in our case, it's N2 plus, vibrational and also rotational spectroscopic transitions are not electric dipole allowed because there is no dipole moment in the molecule. So in this case, what can one do? These transitions only become allowed in higher approximations, higher order approximations, right? And the next higher order approximation, at least when it comes to the electric part of the problem, is the electric quadrupole approximation. So these vibrational transitions, they become allowed by quadrupole coupling of the molecule with the radiation. And but these transitions are then extremely weak. To put this into perspective, such typical quadrupole vibrational transitions are about 10 orders of magnitude weaker than strong dipole allowed infrared transitions in polar molecules. So they are extremely weak, but for the same reason, they are also extremely narrow and therefore interesting for precision measurements. And as a matter of fact, nitrogen has been proposed as a good system to test time variations in MP over ME, right? And it can also be thought of as a good system to implement molecular clocks, right, on this quadrupole transition set. Okay, so a few years ago, we set out to do exactly such experiments to, in the first stage, find these quadrupole transitions in nitrogen ions. And these vibrational quadrupole transitions, they have been measured in neutral molecules, a few, H2, N2, these sort of molecules, CO2 now, not too many, but those few. But to our knowledge, before this work, not in any molecular ion. And the reason are the formidable problems with detecting these extremely weak spectroscopic transitions, even more so in dilute samples as one usually has with ions. So what we did is the following. In the first incarnation of these experiments, we again had sympathetically cooled nitrogen ions in a Coulomb crystal, as usual about 20 to 25. And then we would excite these quadrupole infrared transitions with an infrared laser. In our case, it was a quantum cascade laser, which a highest power that we could get at the time. And we would just irradiate these transitions for a long time in the trap, about 2 minutes. And here, the big advantage of ion traps comes into play, that you can keep the ions for a long time in the trap and therefore realize experiment with very long interaction times. And then we would detect molecules that had been excited again by this charge transfer trick with argon. And that is a schematic of the experiment. We have an ion trap. I should also say how we introduced the nitrogen ions. Didn't say this before. Or the nitrogen molecules. We have a molecular beam, which is interfaced with the ion trap. And then here in the center of the ion trap, the nitrogen ions are then produced by state-selective photoionization using dye laser beams. Then we have laser beams for the cooling of the calcium ions. And then we also have, in this particular case, an infrared laser for the infrared excitation of the nitrogen ions. So also nitrogen is already a molecule with many gory spectroscopic details, right? I really want to spare this at this point, but suffice to say, of course, we have rotational structure superimposed on this vibrational transition again. Then we have spin rotational structure, we have hyperfine structure. So for a spectroscopist, this is all very exciting, but this is not the topic of the talk today. So suffice to say, we did an excitation from the vibrational ground state to the vibrational excited state. We picked an excitation where we start from the rotational ground state and then populate the second excited rotational state, and we were addressing different fine and hyperfine components in this transition. And that is a spectrum that we got in the end. After a long search, these lines are so extremely narrow and weak. As a matter of fact, it took us more than a year to find these lines. And then it took us another couple of months to take this spectrum. And what this spectrum shows here is hyperfine components out of this vibrational rotational line, some of them. And to our knowledge, this was really the first quadrupole spectrum of a molecular ion that had been recorded. So at that time, which is now some 7 years ago, we were extremely proud of this result. It was a very hard experiment. But at the same time, this experiment also shows the problems, right, associated with these technologies, right? I mean, the signal to noise ratio is quite poor here, and that after several months of work. So if one wants to measure these transitions extremely precisely, right, then this is not a viable way to go, right? So we need to improve the sensitivity of the detection scheme here. And I mean, in principle, the detection scheme is very sensitive, right? I mean, because we destroy the molecules, right? We can, in principle, detect a single excitation event, right? Because we can, in principle, in these experiments, we can count single molecules, as you have seen. But at the same time, by destroying the molecules, right? I mean, we then have to restart the whole experiment all over again, right? We have to, expel the ions from the trap, reload them, go through all the state preparation scheme again, right? Do the spectroscopy again, do this laser-induced charge transfer again. This takes time. So one experimental cycle takes a couple of minutes. Yeah. And so the duty cycle of all these experiments, also the photodissociation experiments, is very, very small, because you're always destroying a sample. So there are two ways out of this, essentially. So one of them is, okay, you could say, okay, I need more statistics, so let's use just more particles, right? Fine. That's not what we did. So we did the exact opposite. We took less particles. To be more precise, only one. But then we changed the detection scheme in a way so that it becomes completely non-destructive. And that now brings me to the last topic of my talk, which is molecular ion quantum technologies and their application to spectroscopy. But before we start here, I think it would be another good opportunity to take a few questions, if there are any.
Right. There are none in the chat box. So can I take the liberty of asking one, Stefan?
Sure.
Right. So when you do the charge exchange with the argon, how do you put the argon beam into your crystal and not affect everything that is there already? I mean, it does the charge transfer with the nitrogen. And I mean, what are the parameters that actually you have to keep in mind when you are doing this argon-based charge transfer?
Very good question. Thank you. So the argon is introduced into the experiment by a leak valve. Yeah, and we use only very small partial pressures of argon. Of course, there is the problem that it could affect the molecular ions in a different way as well. Yeah, for instance, by inelastic collisions. But it turns out that, interestingly, the inelastic collision rate between argon and N2 plus is very small. It's only a fraction of the elastic collision rate. So this means that the introduction of argon, right, does on the timescales of our experiment not really change the state of the molecule. And moreover, the whole detection is performed after, in this case, the infrared excitation. But once the charge transfer experiment is done, right, it's of course over, right? I mean, then we have to, reload re-initialize the entire experiment, load again, and then what have you. Does this answer the question, Sadiq?
Yeah. That answers the question. So the partial pressure is like you still maintain 10 minus 10 overall in your...
So we go a few times 10 to the minus 9.
Okay.
In this case, yeah.
All right. Yeah, I think please carry on. There are no further questions in the chat.
Okay, thank you. Okay, then let me come to the my last topic of today. This is molecular quantum technologies for ions and their application to spectroscopy. And now I need to dwell a bit on some details of the quantum motion of the ions in the trap. And I have seen that the Didi Leibfried has already covered this as well yesterday. So I'm very grateful to Didi, because then I can cut this short. So, but just to briefly recapitulate that. So we have an ion in a harmonic trap. Let's restrict ourselves to a single ion in this harmonic trap for the time being. And if you think of it from a quantum mechanical perspective, then, as I've already said, these traps are all designed that they produce a harmonic potential. And so we can think of the whole problem as a quantum harmonic oscillator. Yeah. So the oscillation, the motion of the ion in the trap can be understood as a quantum harmonic oscillator. And then, you can apply all the machinery that you have learned in your freshman quantum mechanics class, right, about harmonic oscillators, right? So we have quantized energy levels of this harmonic oscillator. We have 0-point energy, right? We have equidistant energy levels between the motional states are equidistant on an energy scale, and all these sort of things. So, and moreover, what you can then do is you can start to address these harmonic oscillator levels in your experiment. And you have to think about it in the following way. So now let's assume we have a single ion in the trap. For the sake of simplicity, it's an atomic ion, and we pick two energy levels from this atomic ion, say two different electronic energy levels, a ground state and some excited state. And then on top of that, we have these harmonic oscillator energy levels of the motion of this ion in the potential of the trap. So if we put those two together, right, then if you will, we get something like a quasi-molecule, right? So we have the electronic degrees of freedom of this atomic ion G and E, and superposed on that, we have the motional degrees of freedom, right? A bit similar to the vibrational degrees of freedom in a molecule, right? But here it's the motional degrees of freedom of the ion in the trap, and which are then superimposed on the internal, the electronic energy levels of this ion. So after Doppler laser cooling, such an ion is typically, it's cold, right? Typically, around the millikelvin, if you run your experiment well, or even a bit below that. And but it's not yet in its motional ground state, right? Quantum mechanically speaking. So the 0-point energy in typical ion experiments corresponds to a few microkelvin, right? And you usually do not get there just with Doppler laser cooling. So you have some additional to do an additional step to really cool then the ion down to the quantum mechanical motional ground state of the trap. And one of the ways to do this is, for instance, resolved sideband cooling. And so to quickly recapitulate how this works. Yeah, so now let's assume that after Doppler laser cooling, our ion is in the ground state, in the electronic ground state, but it still occupies some excited motional state, say the state with two quanta in the motion. What one can then do is one can then excite the ion to its excited electronic state, but then drive the transition such, right, that one at the same time, one de-excites the motion by one quantum. And this is called a red sideband transition, because one quantum of motion is therefore eliminated from the system. And then the ion is populated in this excited state, right, with one quantum in the motion. It fluoresces back to the ground state. And as you probably have heard from Didi Leibfried yesterday already, then this fluorescence is most effective in a transition where the motional state is conserved. This is called the carrier transition. And so with it, then we go down back to the electronic ground state again, but then we are in the n = 1 state, right? So compared to here, we have already lost one quantum of motion. Then you can do the trick again, another red sideband transition. Here you go to n equals 0 in the excited state, fluoresce back, and at that point you are then in the motional ground state, and then you have really cooled the ion down to its absolute ground state. So this scheme is called resolved sideband cooling, and this is one of the major schemes which is used to make the ions really ultra cold, at least along one specific mode. Of course, certain conditions have to be met here, and this was discussed yesterday by Didi Leibfried. You have to be in the Lamb-Dicke regime, right? So this means that the amplitude of the motion of the ions to start with must be smaller than the wavelength of the cooling laser that you use here, right? So this is why you need the Doppler pre-cooling. And of course, the bandwidth of your laser must be small enough to resolve these different sidebands. Yeah. And in typical ion trapping experiments in this fashion, right? So the motional frequencies of the ions are on the order of a megahertz, right? So the spacing between these levels is on the order of a megahertz. So you need a narrow band laser in order to resolve these different sidebands. So let me show you a concrete example from our lab. So of such an experiment. So this is an experiment where we have cooled down a calcium nitrogen 2-ion string to its motional ground state. And then that already ties into the later experiment where we then do spectroscopy on the nitrogen ion with these methods. And that is a preparatory step for that. So we have a calcium ion and we have a nitrogen ion. Again, you can't see the nitrogen ion because it doesn't fluoresce, right? But you know it's there. And we can then start to measure a sideband spectrum, right, of this calcium nitrogen 2-ion string. Right? And we do this by exciting the calcium ion on a dipole forbidden electronic transition in this case. So this is the level scheme of calcium ion, in a bit more detailed compared to what I've shown you before. And for this experiment, then one uses a transition from the ground state, the 4s1/2 state, to the excited D state. In particular, specifically the 3D doublet D5 state, which is around 729 nanometers. So this is a dipole forbidden transition, right? But it's allowed in the quadrupole approximation, right? Because the L quantum number changes by 2 units. So it's quadrupole allowed. So, and this is at 729 nanometers. It's a narrow transition, and we use a narrow laser in order to drive this transition. And if you start taking a spectrum of this transition, right, in the resolved sideband regime, then this is what you get, right? You're not only getting one transition, right, per Siemens component even, right? But you get many different transitions, and what you see here what you start seeing here are the different sidebands. And the sidebands correspond then to transitions where you change the motional quantum number by 1 unit. Either you lose 1 unit, these are these red sideband transitions that I've already mentioned, or you increase it by 1 unit, that's a blue sideband transition. And in the middle, you have the carrier transitions. These are these transitions where the motional quantum number is not changed during this electronic excitation here. So if you now do resolved sideband cooling and cool the system down to the ground state of this harmonic oscillator, then this red sideband vanishes. And that is shown here. This is this red spectrum here. Yeah, it's essentially 0, because if you're already in the ground state, you cannot drive another transition where you yet lose another quantum. Yeah, because there's no state below the ground state. Okay, so when you are in the ground state, then this red sideband vanishes. Yeah, and then you really know you're as cold as you can get. And that is, by the way, another method which you can use for thermometry, right? By just measuring the strength of this red sideband transition. Okay, good. So this is now a prerequisite to do both quantum logic and spectroscopic measurements. And in order to explain how this works, I'd like to discuss a very famous experiment with you, which essentially triggered this whole field. And that was an experiment by the NIST group, now done more than 15 years ago, which dealt with the quantum logic spectroscopy of the 27 aluminium plus ion. So aluminium plus is one of the prime ions for setting up optical clocks. The problem with aluminium pluses is that it can't really be laser cooled easily because it has a cycling transition, but the wavelength of these cycling transitions is 167 nanometers. And that is not a nice wavelength to work with. So this means you can't really directly laser cool it. And in these ion experiments, trapped ion experiments, you also always use these cycling transitions for state readout. And so this can't be done here either. Yeah, so it can't be cooled, it can't be properly read out. So what do you do? And in this work, they came up with a scheme which they call quantum logic spectroscopy. And the basic idea behind it is that you do the spectroscopy on this aluminum ion, and the spectroscopy transition that they were interested in, this is the clock transition in aluminum. It's the 1s0 to 3p1 transition. This is the transition that they wanted to do spectroscopy on. So you do spectroscopy in this transition, but you read out spectroscopic excitation on a neighboring beryllium ion. And this beryllium ion is not only used for readout, but also for sympathetic cooling of the aluminum ion. So the detection scheme is by transferring the information on the spectroscopic excitation here to a neighboring beryllium ion and reading it out from there by fluorescence again, because there is beryllium can be laser cooled. It has an easily accessible cycling transition, which can be used for readout. So how does this work? So it starts with cooling both of these ions down to the motional ground state of the trap, yeah, or at least the motional ground state corresponding to one mode of motion in the trap, similar to what I have shown you before in our calcium-nitrogen experiment. And then going through such a quantum logic protocol. And yeah, this uses the following elements. They define two qubits. One of them is in the beryllium. It's called the logic ions. And here, the two qubit states are hyperfine components of the ground state, which are connected by a Raman transition. And in aluminium, they chose as qubit essentially the two levels associated with the spectroscopy transition that they were interested in. So how does this spectroscopic detection scheme now works? So it's a bit intricate, so I'll go through it slowly. So we start by putting both systems, the spectroscopy ion and the logic ion, into the lower qubit states in the motional ground state. So both ions were initialized in these states. Okay, then the spectroscopic transition in aluminium was excited, yeah, taking it to the upper state of the spectroscopic transition, so the upper qubit state. After the excitation, it was de-excited again by a red sideband transition on the spectroscopy transition. Red sideband transition means in this case, if you start with it from the excited state, then essentially it's the reverse. When you start from the ground state, it now adds one quantum of motion to the whole crystal. So, and because these two ions are coupled in the trap by the Coulomb interaction, it's essentially a combined motion of the two ions. So this also means that the logic ion, the beryllium ion, is then excited, is then motionally excited by this red sideband transition. And then they, in the last step, they then shelved the beryllium ion in its upper qubit state, so this excited hyperfine state, by a Raman transition, by a red sideband transition on the beryllium ion. But this only works, right, if the motion has been excited by this red sideband transition on aluminium to start with, right? That is the condition. So essentially this means is that at the point where this beryllium ion has been shelved in this upper qubit state, then the fluorescence breaks down, right? If they start interrogating it by fluorescence, right, then they don't observe anything because the beryllium ion has been shelved in a different state. And this only works if, again, if the motion has been excited beforehand. And this is only the case if the aluminium ion has been excited on a spectroscopy position beforehand, okay? So in this way, information about the spectroscopic excitation of aluminium is transferred to beryllium and then read out from beryllium in this rather elegant manner. Yeah, and this is what was the first experiment on what is now called quantum logic spectroscopy. So they then used this scheme to to ask some rather fundamental questions, right? For instance, they measured this transition in aluminium for for more than a year, and used this to constrain a time variation of the fine structure constant alpha over that year. And what they found is that, okay, within their measurement sensitivities, then they didn't find any statistically significant time variation of alpha in this case. But this again, this shows an application of these highly precise spectroscopic measurements within the realm of changing fundamental constants. Okay, so that happened already some 15 years ago. And then it took more than 10 years to apply these sort of ideas and techniques to molecular ions, right? And again, the problem is the increased complexity of molecular systems. And the first experiment in the realm of quantum logic spectroscopy of molecular ions came from Pete Schmidt's group, who was also involved in the first quantum logic experiments on aluminium some 5 years ago. And let me now quickly walk you through this to see how this works. So in this experiment, they also used magnesium hydride plus as the molecule that they wanted to study. And they were and they wanted to do a quantum logic spectroscopy readout of in this case, an electronic transition in magnesium hydride. So the experiment was like they had magnesium plus as the logic ion, which also served for the sympathetic cooling and resolved sideband cooling. And then they had magnesium hydride plus, which they wanted to probe spectroscopically with these quantum logic techniques. So the scheme here is a bit more involved. What they did is they implemented an emotional qubit in the following way. So what I haven't told you before is that these ions, they have different modes of motion in the trap. It's not a one-dimensional harmonic oscillator, it's a multi-dimensional harmonic oscillator. If you have two ions in the trap, you have in total 6 degrees of freedom, so 6 different modes. And if you just think about the oscillation along the symmetry axis of the trap, you have 2 modes. One of them is the in-phase mode, right, where both ions oscillate in phase. And then there's the out-of-phase mode, where both ions oscillate out of phase. And they then implemented emotional qubit in these modes, defined in the following way. The down state is the one where we have 1 quantum in the in-phase mode and 0 quanta in the out-of-phase mode. And then the up state is where we have 0 quanta in the in-phase mode and 1 quantum in the out-of-phase mode. And then they overlaid this ion crystal with an optical lattice. So focused counter-propagating laser beams. And this lattice was modulated at the frequency which corresponded to the frequency, to the difference of the motional frequencies of this out-of-phase mode and of the in-phase mode. So what this optical lattice did is its wavelength was chosen such that it was closely detuned from an electronic transition in the magnesium hydride ion. And in that way, so it was not on resonance with this electronic transition, but it was closely detuned from it. So in that way, it was prevented that this optical lattice, this laser beam, excites the molecule, but it was close enough detuned so that it would still produce a strong enough optical dipole force on it. Yeah, so an optical dipole force is generated by this dispersive interaction of this laser beam, in this case with the molecule. And the strength of this interaction, yeah, I mean, you can call it an AC dark shift or a light shift, all boils down to the same phenomenon. This dipole force that is generated by this optical lattice is the stronger, the closer the system is detuned from a spectroscopic resonance in the molecule. So this is where the spectroscopic information comes into play. So what they then did is that whenever this optical dipole force was acting, meaning if the molecule was in the right quantum state in order to drive, in order to be closely detuned from this electronic transition, this optical lattice which was modulated at this difference frequency would then induce a rotation of this qubit. Can visualize this with a Bloch sphere picture. So this optical dipole force would then rotate the qubit from on the Bloch sphere as a consequence of this optical dipole force. Because this modulation would then actually lead to a, if you will, a sort of excitation of these motional modes, and therefore a rotation on of this qubit. And moreover, so the problem here in this experiment was that the optical dipole force was acting on both particles, on magnesium plus and on magnesium hydride plus. But the rotation was more pronounced than when the magnesium hydride plus was also in near resonance with this optical lattice. So this would then entail a stronger or a more pronounced rotation of this qubit. And this could then be read out again on the magnesium ion. And moreover, one could then read out or determine the rotation of this qubit as a function of the detuning of this lattice laser from the spectroscopic transition in magnesium hydride. And in this way, from the strength of this rotation, in the end, then map out the spectroscopic line shape that is associated with the transition from which the optical lattice was closely detuned. So that is, in a way, an adaptation of these quantum logic techniques to the world of molecular ions. It's a bit more involved than in the atomic case. Here they were really working with coming up with a molecular qubit that was constituted from different motional modes and inducing qubit rotation by an optical dipole force that was generated near a spectroscopic transition in the molecule. And then working back from this qubit rotation to the strength of this optical dipole force, and then measuring this qubit, and then measuring the tuning of the lattice laser from the resonance, and thereby gain spectroscopic information on this on the molecular ion. So a similar experiment has also been implemented in our group recently on nitrogen plus in maybe a bit a more simpler fashion that does not need the implementation of such optical qubits. In our case, motional qubits. In our case, we were using a coherent motional excitation of the two ion string induced by such an optical dipole force. And just to also quickly walk you through this experiment, we have two ions in the trap, a calcium and the nitrogen ions. We ground state cool them again, here only in one mode, the in-phase mode of the calcium-nitrogen spring. And then we also introduce an optical lattice, and this optical lattice laser wavelength is closely detuned now to a strong electronic transition in the nitrogen molecule. We would then modulate the lattice laser frequency by the motional frequency of these two ions in the trap, right? And this then, and if the optical dipole force acts on the nitrogen ion, and this is of course only the case if the nitrogen ion is in a very specific quantum state, from which it is near resonant then on this spectroscopic transition, then this modulated optical dipole force would induce a motional excitation of the ion string again. And it's not a simple heating, it's actually a coherent excitation, because it's a coherent drive that is exerted by this modulated optical lattice. So we would then therefore excite the motion of the ions again, and then one can read out this motional excitation by doing Rabi thermometry, right? So driving red sideband transitions again on the calcium ion in this case. And if no motional excitation has happened, meaning if no dipole force has acted on the molecule, then we are still in the motional ground state. And so we do not observe any Rabi oscillations on this red sideband transition. However, if motion excitation has happened, then we observe Rabi oscillations on the sideband transition. And so this means that, and from the amplitude and from the frequency of these Rabi oscillations, we can then work back on the strength of this optical dipole force, and therefore from the detuning of the lattice laser from the spectroscopic transition. Yeah, this gives some more details about the energy level structure of nitrogen that is relevant here. I already said we have we use a strong electronic transition in nitrogen. Actually, it's exactly the same transition that we previously used in this laser-induced charge transfer experiment. Only here we use it for generating an optical dipole force. Again, we have different rotational components, and we were focusing on a case where we prepared the ions in n equals 0 and j equals 0, so in the absolute ground state of the molecule, particularly rotational ground state. And then these blue curves here shows the strength of the optical dipole force as a function of the detuning of this lattice laser. We would then put the laser frequency very close to the center of this profile here, where in the center we have the resonance condition. So we are very close to the resonance to create a strong optical dipole force in order to perform this experiment in the end. So this can also be used to read out and detect the quantum state of the molecule, right? Because this only works if the molecule is really in the rotational ground state. And if one does a bit of statistics, then one realizes that one can do a state readout measurement here with a fidelity of more than 99%. Yeah. And so this can be done very sensitively. And the reason is, and you can do this because it's completely non-destructive. Yeah. So one does not destroy the molecule in this readout scheme anymore. One not even changes its quantum state, right? Because it's a completely dispersive interaction in the end, right? So we do not excite the molecule really, right? We only, create an optical dipole force close to the resonance. Yeah. So it's chemically non-destructive and quantum non-demolition. So we can recycle the same molecule over and over again, and in this way boost the duty cycle of the experiment by, in our case, 4 to 5 orders of magnitude. Yeah. And that is way more sensitive than any destructive detection scheme that has been used before. Okay, good. So I had to speed up a bit in the end in order to not take up too much of your time. So I'm essentially finished with this part now. I should also say that there are now, this is now a new and growing field, this molecular ion quantum technologies. There are already a range of other exciting experiments as well, for instance, from the NIST group, where they also did various types of spectroscopic experiments and also quantum entanglement experiments with atomic ions. And so this is a field that is really just starting at the moment. And I believe that many more exciting developments in this realm can be expected in the very near future. Okay, so this brings me to the end of my lecture today. And I'm happy to take any further questions if there are any.
Yeah, Stefan. So the thing is that we have overrun the time a bit. Okay. So I have recorded the questions which are pending. How about we start your next talk with answering some of those questions and then move forward?
That's fine. Yeah, we can do that.
Right.
So we can address these questions
not to kind of intrude on the next talk. Okay.
Okay. I already see Christoph here. Hello, Christoph. Yes.
So over to you, Sourav. You can just give some instructions, maybe.
Yeah, thank you for the talk. So I guess, I mean, you could, in principle, take a couple of questions until because it doesn't start in 6 or 7 minutes. If Professor Willitsch is over.
Okay, let me ask you the questions then, and if you want to take a timeout, can take a timeout.
Yes, that's
right. So sideband cooling is radial, I guess. So is it possible to do it from the axial direction also?
In our case, it's actually axial. But yeah, I mean, you can do this from any direction. Yeah, in principle.
A related question is, what is the time scale of quantum logic protocol technique?
So one complete cycle takes 20 to 30 milliseconds in our case.
Right.
Yeah. So one single readout experiment takes 20 to 30 milliseconds.
Yeah, so another question.
Previously, it has taken about 10 minutes. And that's the big advantage of the scheme.
Right. That's when you were not doing the quantum logic.
That's right. Yeah.
Yeah. Okay. So for two ions in the same trapping well, how does the Coulomb repulsion affect the motional states, perturbatively or non-perturbatively?
Yeah, that's something I didn't really go into the detail, and so I thank you for this question in order to clarify this. So essentially, you can't. It's a strong interaction, so you can't really treat it perturbatively anymore, right? So you really have to treat it as a strongly coupled system, and you have to think in terms, really start thinking in terms of normal modes of the ions which are coupled by the Coulomb interaction in the trap. So it's normal modes, meaning that the motion of the ions is really highly synchronized, right? And this is what I showed with the example of the in-phase and of the out-of-phase mode, right? So you have an in-phase mode then of this two ion string where both ions then essentially oscillate in phase together, right? And the out-of-phase mode is then they oscillate against one another. So you really have to treat these as a strongly coupled system. And again, one can make an analogy with molecules here, right? In which the atoms are also strongly coupled together in a molecule, right? And you also have to think here of the vibrational modes in a molecule. You have to think of them in terms of normal modes.
Right. I think I don't see any further questions. So if yeah, so I think we can thank Stefan for a lovely presentation and look forward to his next one. And meanwhile, I will hand it back to Sourav, who will then kick off the next session.
Sure. Okay. Thank you, Sadiq. Thank you, Professor Willitsch. So we will see you again on day after tomorrow. So the next session will start in maybe 3 minutes, and Bodhaditya will again introduce Professor Nägerl. So I just want to start at that given time so that nobody misses the beginning of the talk. Gobi, could you unmute the next session chair, Bodhaditya Santra? He cannot unmute himself.
Oh, yeah, sure, sir. His name, professor name?
Bodhaditya Santra. BODHA.
Yes. Okay, now he can.
Okay, thank you.
Yeah.
Okay, Bodhaditya, so you take over then.
Okay, yeah, I can do it now. Thank you, Sourav. And thanks for allowing me to unmute.
No, it's fine. Great. Yeah, I forgot actually.
In the next, yeah, no problem. I think the next speaker is Professor Hanns-Christoph Nägerl.
Yes.
Let me check whether he's.
Yeah, he's here. I can see him. So maybe a short, very short, brief intro is fine because we already had it last time. So.
Yeah. I think we don't have to make any. Maybe
no need to do another introduction. Yeah.
Yeah, but we do need a session chair. So. Yes.
Yeah. We have a very nice background. Okay. Shall we start now or shall we wait for one more minute?
Yeah, just wait a minute. Somehow I see that like 4 or 5 participants joined, so maybe people are studying. Okay.
Okay. Probably now. Yeah.
Yeah. Okay, he's back. So go ahead.
Okay. So so today Professor Hanns-Christoph Nägerl from University of Innsbruck in Austria is going to deliver his second lecture. So Professor Nägerl, so please go ahead.
Okay. Thanks a lot. Yeah. So also I listened to Stefan's talk just a few minutes ago. Yeah, and it actually gave me a lot of remembrances. Yeah, you'll see a little later. Yeah, why. So anyways, ultra-cold molecules. Yeah, so we are talking about here now neutral molecules, and we are talking about dimer molecules. And let me pick up pick up where we left off yesterday. So we are talking about molecules, simple molecules, dimer molecules, as you will see later, that we in fact make out of atoms. And here's the list of reasons why we do this. And Stefan Willitsch just gave you a few more reasons why this is interesting. I don't go back to that. So just the case of rubidium cesium. Here is the full Hamiltonian, if you wish. So you in principle can control the position and the angle of the dipoles. In principle, you could also think about whether you can actually have different directions of polarization for the molecules, but I think that's difficult to realize. But anyways, rubidium cesium has a well-sized dipole moment, on the order of 1.3 dBi. And that's, I think, very nice for the lab because you don't need that high electrical fields to polarize the molecule. What other options are there? We briefly had this slide already yesterday. KRB is an option, a very nice option. It is it has the possibility that this is a fermion actually. When potassium is a fermion, then the KRB molecule with rubidium being a fermion will be a fermionic molecule. Situation is similar to KCS, where cesium is the boson and potassium can also be a fermion. Admittedly, in Innsbruck, we are working hard on actually still the bosonic version, where potassium-39 is being used. I won't report about that at all, but we're working hard and hopefully at some point we have some results. One very nice molecule, dimer molecule that I should mention that has a very high dipole moment is lithium cesium. And it's being pursued, as far as I know, in Heidelberg and in Cheng Chin's group in Chicago to some extent, but I don't know how far the efforts are towards turning these into ground state molecules. And a bit off this line is rubidium strontium, because strontium is not an alkali, it's an earth alkali, as you know. And so this is it's already opens up a different route, because rubidium strontium now is a molecule with not just magnetic with not just an electric dipole moment, but also with magnetic dipole moment because of the rubidium atom and the strontium electrons being paired up. So that's actually also a nice option. Turns out that this is for sure not easy. The resonances to produce rubidium strontium seem to be rather difficult to handle, rather narrow, but I think we will see some results there also in the near future. Yeah. So, and then for testing purposes, we have also been working here in particular in Innsbruck with homonuclear molecules, and I will come to that briefly because, yeah, I mean, it's a simpler system, yeah, but we, in fact, were able to achieve good control quite early on with a particular cesium-2. Yeah, so anyways, yeah, so let me just remind you what we mean by a molecule. So I will actually talk about the weakly bound molecules, or basically atom pairs, in a second, with a very large internuclear distance, basically set by, if it's an atom pair, it's set by the size of the trap. And that's actually already quite tight, 15 nanometers in a lattice trap. That's the typical scale. But we want to create molecules in the very ground state, and the very ground state means comic, certainly here. You'll see a bit more precise potentials in a second. In the low vibrational ground state with the size of angstroms and a binding energy actually of roughly half an electron volt. Yeah. So what we will have to do is to turn our atom pair into this tightly bound, chemically bound, covalently bounded molecule. Yeah, so here is what we did over the years in Innsbruck. This is now a bit focused on our Innsbruck endeavors. This everything started with turning molecules, atom pairs, into weakly bound molecules. This is started in 2003, and I should say, I think in the school should say these comments. It actually started a bit like an accident. Yeah, we found by accident that our atoms in the BC were actually, we found that they were quite stable in the beam of our multi-frequency laser, trapping laser. But the weakly bound molecules actually that we then produced were actually not stable. And it's not because of collisions, as I will detail in a second. The loss was really quick, and that actually brought us to the idea, well, this molecule, these weakly bound molecules actually are susceptible to optical transitions. Okay, so now we have to remove that binding energy, and that's actually when we had first results on homonuclear molecules in 2008. And it's been since then an endeavor, and it's still ongoing, certainly. Yeah, actually, I think the real high times will only come now and soon. Yeah, and actually, I mentioned that already. You will hear nice, very recent results from Juni tomorrow. So now let's focus quickly onto this ground state. It's a bit more complicated than the picture here. This is certainly the vibrational ground state. Yeah, is indicated in this comic. But it's also, there are also rotational degrees of freedom. Yeah, that's actually certainly very nice, very helpful. But on top of that, there's hyperfine structure. So this is now the example of the homonuclear cesium-2 molecule, but you take any other molecule, KRB or rubidium cesium, and it will have a few dozens of nuclear states. Yeah, so hyperfine states due to the nuclear non-zero nuclear magnetic moment. And that's the manifold of these states. And in the end, what we are interested in is populating one of these states. In fact, that's doable, even though this energy scale, if you look vertically, is only on the tens of kilohertz sort of level. Yeah, but our transfer scheme is selective. Our initial state is well polarized and in a specific hyperfine state. And so we can, and then selection rules help also. So usually transfer only, the transfer that we'll be talking about addresses only 1 or 2 or 3 or so of these levels, and that actually helps. Yeah. So, but anyways, yes, you have to, you can certainly start playing tricks with this ground state molecules, and I believe that Martin Zwierlein will talk about this more, about coherence in these states and driving radio frequency or microwave transitions on these molecules. So let's come back to rubidium cesium, yeah. And this is the specific situation. This is the ground state singlet potential, this triplet potential. Our initial Fetchback molecule that we create, as I will show you in a second, is mostly a triplet molecule, it turns out. And we have to convert that triplet molecule into a singlet ground state molecule, where we then have a sizable dipole moment. Yeah. So when I say on or off, off is off dipole moment, on is in the ground state. And this is the specific situation. We use an excited level with an energy above threshold here of about 6,000 wave numbers. That gives a wavelength around 1,570 nanometers up here. And then we go down, quote unquote. You will see how we do this. Actually, we never populate the state up here. Yeah, we do this in a two-photon way without excitation of the intermediate state. This is done at about 980 nanometers. So that's, let me simplify this. So I'm certainly omitting all the other vibrational levels and so on. So in the end, we will be addressing a specific hyperfine state of that excited state potential. Actually, it's this singlet triplet mixed AB potential that we're using here. This is an important detail in the end, because this, it turns out the state is strongly mixed and actually allows us to convert the triplet molecule into a singlet molecule. Yeah, so we need this accidental mixing here. I call it accidental because it's that's the way nature does it. Yeah. So, and we are choosing a suitable level here where we expect a large mixing, and where we also, just from eyeballing the transitions, where we see that there are strong Frank-Condon factors. Yeah, so I haven't drawn any wave functions here, but you can already imagine that the inner turning point of this level will match with this turning point. So this molecule actually here, the wave function will have 4 areas where its amplitude is enhanced. Yeah, whenever it sort of hits these molecular potentials, loosely speaking. And so we are actually using this enhancement here and there on this inner well here. Yeah, but you see this is an avoided crossing well. Yeah, so it actually caused by these 2 potentials. Anyways, yeah, so that took us some time to figure that out and to do all the spectroscopy and to be a bit lucky to find the right level. And in fact, for KCS, we still need to identify a similar situation. We haven't done so. Yeah, so KCS is still in this sense open. So these are the 2 lasers, and I will just call the final state off. The final state on, the initial state is off, and there is this excited state in between. Now, how do we do this now? Yeah. Okay. After all this preparation. Yeah. So, and then the question is, can we make a condensate, a Bose-Einstein condensate of these ground state molecules? Yeah. So, let's go back to atoms quickly. And we just heard from Stefan Willitsch that atoms are simple and molecules are already significantly more complicated. So if you think about atoms with their simple fine structure split fine structure split excited states, you can find string transitions and do laser cooling, and even the hyperfine structure indicated here is not hurting you. Yeah, you might need a repump laser, but in principle this works for a quite large class of atoms, and it's possible because we have we can recycle our atom all the time. Yeah. So, and this works with many atoms by now. Yeah, I mean, it's just certainly a fraction of the periodic table, but a significantly large fraction. Yeah, and if we go to molecules, we have this comic here where we have a lot of vibrational levels plus the structure that I just discussed. And so, when you do an excitation, you are very likely to de-excite into some other level, and all your population will go away. Yeah, so that's for sure difficult, and we just heard from Stefan Willitsch in his talk what one can do to some extent. Yeah, well, he's not cooling, he's not doing the initial coolings. He was talking about the situation where you already have trapped atoms or trapped molecules, and where you then want to interrogate them. Yeah, so Let me briefly remind you of what endeavors are there around for slowing and cooling molecules. Stefan mentioned some of that already. So one way that people are using is for polar molecules is what is known as Stark deceleration, pioneered by Gerhard Meyer. And actually, he's now back to Berlin. Yeah, he was away from Berlin for some years. He's now back. And this is a Stark decelerator, molecules coming out of an oven or a source here and being Stark decelerated as they move downstream here across 1 or 2 meters. And in the end, they can actually be trapped in, for example, electrostatic trap. Yeah. So that works. That's been demonstrated. That can be augmented or combined with buffer gas cooling, where you have preferentially helium buffer gas to cool your molecular source, yeah. And that has been demonstrated for some molecules with actually fairly large magnetic dipole moment. And the pioneering experiments have been done at Harvard in the group of John Doyle, yeah. But temperatures so far are rather high, yeah, in comparison to what we are aiming at in the millikelvin regime. And one for sure has to combine this with additional techniques. Yeah, so this won't work alone. And in particular, the densities are not high enough. Yeah. So we just heard from Stefan Willitsch that you can do this also in ion traps with ions. Yeah. Well, ions will not condense. Yeah. I don't think it's possible to overlap the wave functions of ions. It's actually an interesting question, yeah, but I don't think ions can be condensed, but you want to, when you want to control them, actually you can do a lot. We just saw here pictures from the Drevsen group in Aarhus with magnesium hydride, for example, being co-trapped in this trap, in this ion trap. And also here, the temperatures are at best in the millikelvin range, yeah, in the millikelvin range at best. We just heard from Stefan how one can do sideband cooling, and so there are avenues, but this works on very small samples. And just for the record, because Stefan mentioned that, when I was a PhD student 25 years ago, we already saw co-trapping, most likely of calcium hydride in a calcium ion trap. We actually learned how to purify it, yeah, how to kick out these molecules, because we co-trapped up to 50%, yeah. But we were interested in just a few calcium ions for quantum computation purposes, and you will hear about the ongoing experiments with calcium ions in Innsbruck from Christian Rose, in fact, yeah. But the old history, long time ago, when I was a young guy, we already saw this. And then, you know, and that's also good to hear from the students, yeah. Then somebody told me, oh, this is all well known. It's been seen in the Wineland group. Forget about it, yeah. So I forgot about it, but I put it, we didn't write a paper, but we put it in my thesis at least to say that there is something going on in these ion traps that's more interesting. And as you see, it by now is an entire field. So, and then you can co-trap ionic molecules and neutral atoms, yeah, overlap, for example, an ion trap for barium chloride ions with calcium ions. And that's been done in the Hudson group at UCLA, for example, and at some other places. So that's also a possibility. Yeah. And in fact, let's see how, actually, I don't know, but Johannes Hecker-Denschlag at this meeting will, I'm sure, talk about more of this. Yeah. So, but even also here, temperatures are rather high, millikelvin. Now, direct cooling of molecules has seen quite spectacular development over the past years, starting with the experiments in the group of Dave DeMille, that being picked up by the group of Mike Tarbert at Imperial College in London. And here's a highlight, this paper on molecules cooled below the Doppler limit. And this is a special molecule, calcium fluoride. It's what we call a diagonal molecule where one has essentially cycling transitions. Yeah, and this will probably be a very nice route to pursue also. Yeah, and that has a lot of possible applications. Yeah, so temperatures are below millikelvin for these experiments. They go into the microkelvin regime nowadays in recent years, but admittedly, the density is still rather low. So the phase-space density, PSD, is rather low still, yeah. So certainly, I'm hopeful that this will also yield to high phase-space densities in the end. So what's the phase-space density? Well, as you all know, the product of the thermal wavelength and the density. And as you know, we want to push these experiments towards phase-space density of unity into the regime of quantum degeneracy. Yeah, so you have to watch both. The particle density has to stay high, and the relatively high, and the temperature has to be low. Yeah, so we have to do tricks to reach high phase-space densities. Yeah, and then to not lose, as I always say, yeah, phase-space density. So now you can say, well, why not start from ultra-cold atoms? In fact, that's been also an endeavor that's been going on for quite some years. Actually, the photoassociation is a nice way of going from ultra-cold atoms to ultra-cold molecules, and this has been done over more than 20 years by now. Yeah, so one can do this in a one color scheme, where you just have one laser, and then spontaneous emission takes you into some bound state, molecular bound state, or you can do this in a more controlled way, where you have two lasers, and you do either a pump dump scheme or perhaps something more clever, as I will talk about later. Yeah, in principle, this looks good. Yeah. But it turns out, for whatever reason, yeah, one can speculate a little bit, the densities done in the typical experiments, even in the ultra-cold experiments, and have not been really persuasive. Yeah, so this has not worked so well, and actually, I don't know why. Yeah, I have to admit, we've never done photo association. We'll do something else in a moment. So we actually do Fetchback association. We've not systematically done that. I know that some groups have played with photo association, and it works okay, but it has some limitations. Yeah, so one should say, and perhaps somebody else will demonstrate a better way. The densities are still rather low. Yeah, even though one essentially inherits the initially low temperatures from the atoms. Yeah. So, but I'm confident this will work out better in the future. Yeah. So now, what's the other way? Is actually, I mentioned already, is going via so-called Fetchback resonances, and we already discussed what Fetchback resonances are. And this shows a result from a long time ago, where we have a Bose-Einstein condensate, and we outcouple from this condensate a cold sample, very cold sample, actually a sample in the regime of quantum degeneracy, initially at least, yeah, of molecules, yeah. And actually, but not trapped, actually expanding very slowly with very low rates, comparing rates at the level of nanokelvin, actually, yeah. And we call these molecules, because they are produced on the Fetchback resonance, we call them Fetchback molecules, although in our case, they're nothing else but van der Waals molecules. Yeah, this is the van der Waals tail of your molecular potential, and we call them Fetchback molecules. So now let me simplify the Fetchback resonance that I've shown earlier, just as a level crossing. Yeah, so here I plot the energy of two atoms horizontal, and the molecular energy to have some tilt. There's a certainly, I mean, it's only interesting if there's a difference in the magnetic moment, and the intersection point is essentially this Fetchback resonance. Yeah, so as indicated here, as discussed earlier. Yeah, and so if you zoom in into that intersection point, there will be an avoided crossing. Yeah, so you have a sort of a situation where you mix your atomic state with the molecular state, and if you then go away from the resonance, you actually acquire some binding energy, and you actually create a molecule that's very weakly bound. Yeah. So this avoided crossing is in fact our entrance door into the molecular world by dynamically changing the magnetic field here in this picture from right to left. Yeah. In this case, for this particular resonance, from higher field to lower field. Yeah. So that's our entrance door, yeah. And in the experiment, we have an atomic sample here, just shown schematically, and we ramp across the resonance as a certain fraction of the atoms finds a partner and that gives us a certain molecular fraction. When you do this in free space, the typical efficiencies are a few percent, up to 10%. And if you push it a bit, we've seen efficiencies up to 40%. But then, but that needs free space and another trap we've seen. Yeah. So from a BEC of 100,000 atoms, let's say. Yeah. So, but in any ways, that's very nice. So this is actually the picture that I just showed you before. Actually, what's being done to record that picture? Actually, we go back in magnetic field. And we bring the molecules above threshold. The molecules will dissociate back into atoms, and then you image them. Yeah. And how do you separate? Yeah, the molecular part from the atomic part. Well, this is done in a Stern-Gerlach type experiment by means of a magnetic force, so we apply this magnetic gradient while we have them after production, and then this force separates the two samples, and then you can, for example, remove the atomic part with usually a combination of microwave and light into other states, and then it's not resonant anymore with your imaging light, and then we get a picture like this, yeah, with only the molecular part. Here, certainly, I just did a PowerPoint picture, yeah. Okay, anyways, yeah. So this is the way it's been done now for the past more than 15 years. In various groups, and this is a gallery of the initial homonuclear molecules being produced in this Fetchback way. Yeah. Okay, so what are the properties of these Fetchback molecules, you might ask? Yeah, so we are actually here in one of the very last bound states. I showed you a spectrum of states already earlier, Rubidium Cesium. Yeah, I'll come back to that. Yeah. So all these pictures here certainly are didactic. They are simplified. Yeah. Anyways, we are in a single rotational quantum state. Yeah. It's highly excited. It's usually the -1 state. Not quite sometimes, yeah, but it's effectively the last bound state. We count them from threshold. Rotationally, they're usually very cold. Yeah, they are typically they're S or perhaps P or D, depends a bit on what you're doing, but they are rotationally very cold. And all this has been demonstrated. So when I say BB is Bose-Bose or Fermi-Fermi or Bose-Fermi, different ones, you can actually create all kinds of end-over-end angular momentum for the molecule, yeah. And they are the binding energy is very little, kilohertz, megahertz, and perhaps then gigahertz, yeah, if you go further. And you can use further avoided crossings to take your molecules to lower lying states, but it's still a very weakly bound Fetchback or van der Waals molecule, yeah, for all practical processes, yeah. So what are the relevant processes that these molecules are subject to? That's actually collisions, yeah. So atom-molecule collisions play a role while we create the molecules initially, because there are still atoms around, and when we then have a molecular sample, we have to worry about molecule-molecule collisions. And when I say worry, actually, that's what we want. We want interactions, yeah, because we want to create an interacting gas in the end, yeah. So, but the first problem that arises from collisions is that collisions lead to relaxation, yeah. So molecules collide and relax into a lower lying state. And in fact, I'm pretty sure that Johannes Hecker-Deinschlag will talk about this later in this workshop. Yeah, so you have here in my comic a collision between an atom and a molecule, and that will release a significant part of the binding energy. Usually the decay is not into the very ground state, but it's actually a decay in one of the nearby levels. I think the argument is basically a Frank Condon type overlap argument. Yeah, so you create still a molecule that's still very weakly bound, but you remove a few megahertz of binding energy or gigahertz, and that's already enough to kick out these molecules from our trap. Yeah. Our traps have tens of kilohertz binding energies typically. Yeah. So actually seeing this was the first publication on this loss. I should mention that was from the MIT group of Wolfgang Kerterle, seeing loss of molecules in the trap, and I just want to give this as a reference. Yeah, I have to say certainly we saw this also very quickly in our experiments. Yeah, And so Wolfgang Ketteler documented the molecule-molecule loss and the atom-molecule loss in his trap. So why is this relevant? Because let me come back to the creation. When you create the molecules, we have to go adiabatically across the resonance. So we cannot do this at infinite speed. There's some time scale associated with that. And so there is time for the molecules to collide, the newly formed molecules to collide with the atoms then, right? So that's actually the problem. And so either you make sure that you don't have any other atoms around anymore, yeah? So the ideal situation is where you just have 2 atoms per site, and per well, per trap, and then there is nothing else to collide with. Yeah, so that's the idea. Yeah, so that limits the lifetime, and if you have more than 1 atom at any well in your trap. Yeah, so an obvious solution is use an optical lattice. Yeah, so trap your molecules inside a situation where you can localize the atoms and make sure that you only have few atoms per lattice site, ideally exactly 2 atoms per lattice site. Okay, and then you end up with 1 molecule per lattice site after doing the process. Yeah, so this is in fact what I already told you. I'm just coming back to this comic of mine from earlier, where we mix and we create atom pairs in this lattice as indicated here in step 2. Yeah, so and only then we create the molecule. So that step now then from 2 to 3 is the one that I just discussed, and that should work well. So now let me come to step 3 to 4. Yeah, so this ground state transfer. Yeah, so this should be briefly mentioned because it's important for everything. Yeah, you saw this picture here already earlier. This is the case of Rubidium Cesium again. I'm not detailing exactly this initial state here. Yeah, I don't have the time, this specific hyperfine state here. I'm not showing any details here. But basically, we are lucky. This is essentially a 3-level system, perhaps with some spectator levels, in particular up here. And one can be lucky or unlucky. I think we've been lucky with this choice of our states. And so how does this work? And let me just remind you of your basic atomic physics. If you have 3 levels, there's 3 levels with 2 lasers on resonance. And that's actually only what you need. You can immediately write down the matrix, the 3x3 matrix, and you will immediately find that one of the solutions, the eigenstates of that problem actually has this form. It's a dark state because it does not involve the excited state. Yeah, so we assume the excited state has some loss rate gamma that is non-negligible. Yeah, that so we want to avoid that excited state. And the solution is this interesting combination between the 2 ground states. Yeah, this coherent superposition. And I think if you've never seen it, I think it's almost evident that with 2 lasers on resonance, you create this kind of superposition state. Yeah. And if you want to learn more, this is a good review from Nikolai Vitanov. So omega are the Rabi frequencies, the coupling strengths on this transition. And as you know, it's a product of the dipole moment and the electrical field. And I don't go into any of the details, but in fact, the problem with molecules is, if I go back here, you have to obey the Frank Condon principle. So these dipole moments are rather weak. Yeah. So that actually is important to know. Yeah. So these Rabi frequencies are not that strong in view of the fact that these dipole moments are not infinite. Yeah, and they are not atomic. And they are strongly suppressed because of the overlap of the nuclear wave function. So and also you cannot crank up the electrical field too much, because at some point you run into other problems like Stark shifts and so on. Yeah, so there's a compromise at some point what you want here, but it turns out it works all nicely. Yeah, so rotating now from the initial state 1 into the final state 3, in view of this interesting superposition here, will require you to turn on the second laser first and the first laser then afterwards. So explicitly, this is no pump dump scheme, but it's really a coherent transfer from 1 to 3 with this counterintuitive pulse sequence. Yeah. So you have to have a sizable overlap of these two light pulses. Yeah. I don't go into the details here now, but basically what happens is that laser 2 creates an outer town splitting, and then omega 1 mixes in these states and then rotates the state from 1 to 3. Then when you do this, populations will change as indicated here in this comic. I'm going to show you data in a second, from 1 to 3. And this is all well known. It's been used in molecular spectroscopy, usually by going the other way around, going from ground state molecules, but without any rotational control, for example, in a molecular beam, to go into more excited states. We are doing this now the other way around. And using it for full state control. And also for the young students, when I proposed this long time ago, an eminent physicist that came to our lab said, not gonna work. Okay, well, it works, yeah. So, okay, the person was right to some extent because there were things to watch, yeah. Because as I said, the overlap integrals are small, and so it's for sure not easy. But in the regime that we work, it actually works really nicely. So, but nothing comes for free, and that's actually one has to be adiabatic, and adiabatic actually means in this particular case that the product of the time over which you do it times the Rabi frequency squared has to be significantly larger than the decay rate. It turns out one can fulfill this, yeah, in view of the fact that usually these excited states, these mixed states, are rather long-lived, yeah, and then this actually can be fulfilled, yeah. And it turns out this 2 pi squared factor is actually there, yeah, and you want this factor to be this on the left by a factor of 10 larger than the right, roughly, yeah. So then this factor 2 pi actually squared does play a role, yeah. So anyways, yeah, I think there's a question already in the chat, but let me see, let me just show you how this works, and then I take questions. I'm happy to take a few questions. So what you do in the experiment, you actually, I go back, you go from 1 to 3, and then you go back for detection, and then you do everything reverse, yeah. So that's the idea, yeah. So we here on the left, you create the ground state molecules. On the right, you go back, and then you dissociate and image atoms, and we detect these Fetchback molecules as I just told you before, yeah. So this works actually really nicely, and as you will see, creation happens on 10 microseconds. Detection happens here within tens of microseconds, and the waiting time can be seconds. Yeah. So, go down, go up. That's what I just said. And okay, perhaps, but before I show you some experiments and data, I'd have a look at the chat.
So there is one question. It says,
there's a question. Yeah, I read the question. Yeah. So okay, yeah, okay. The phase coherence between the two lasers is crucial. Yeah. So while you do this, while you do the transfer, let me you see now it's jammed. When you do this, the two lasers have to be phase coherent. Yeah. So in fact, what we do is we make them stable passively a lot. So while we do the transfer, they are very stable. It doesn't matter from shot to shot. Next time there's a totally new phase, but the difference phase has to be stable while you do this. If it's not, it will actually rotate you out of this dark state and destroy your dark state. Yeah. So this is actually crucial. So you need to do some tricks. You need to lock lasers very well to a high finesse cavity and so on. Yeah. And in particular, if you want to play with a longer time scale here for being more adiabatic, you need longer coherence times. Yeah. So perhaps I say this already at this point. The limits of this have not been tested, I have to say. We see efficiencies in these experiments of 90%. The question is, why not 99%? Well, I think the main reason is because nobody has pushed for it yet. But it's then very stable lasers. So here's a gallery of experiments that have been done. since 2007. Actually, it started here in Innsbruck with 2 endeavors on rubidium and cesium. At the same time, our friends at GILA worked on KRB. And then in 2008, we could actually demonstrate that we can do a transfer actually into a chemically bound state. Yeah. So when we actually showed this, it was clear to me this is going to work, because the second step is not so difficult. It's actually the first step from the weakly bound level to that step. So that was for us the important experiment to demonstrate that this is possible. And that's actually where this colleague said, no, it's not going to work. Yeah, because the step from 0 to 73, let's say, that was demonstrated before the other way around on other molecules. We were confident that this worked. Yeah. Okay, so we could then already produce quite dense samples of molecules. And a little later, our friends in GILA demonstrated transfer to all the way to the ground state with a binding energy of 120 terahertz, half an electron volt roughly. Yeah. So in 2008. So this shows data for the case of rubidium cesium for a sample that is not super cold. It's hundreds of nanokelvin trapped in a lattice though. After production, but not with full control, not in the lowest band of the lattice, and the single pass efficiency here is usually on the order of 85 to 90%, and this is the publication down here where we demonstrated that. And this was done on a sample where the filling fraction in the lattice was 2 or 3% or so. Yeah, so rather low. And okay, but that and the holding time is rather short. Here is just 15 or 20 microseconds. Okay, so this is the situation for rubidium cesium. Yeah, so now I still have to tell you how to produce the pairs up here. And I see there's another question in the chat. Let me see. Yeah. So the question is it possible to bypass the step of magnetic Fetchback isolation and to do stir-up from atoms to molecules directly? Yes, this is actually, there have been demonstrations of this. Actually, one of the Japanese group has been working on this, and the efficiency is okay, but not very high. So it turns out I think if you want to push this towards really high efficiencies, we probably have to do it via the Fetchback step. Yeah, I mean the advantage of doing Fetchback, the optical transfer from the Fetchback situation is that the Frank Condon elements already are much better. Yeah, so that's what we found, and that's what I think still needs to be demonstrated that this works otherwise. Yeah, with similar efficiencies. Okay, so okay, this is back my comic now. Okay, when I actually call this, I have to. So it turns out this mixing is difficult. So let me do a quick diversion and tell you how we did this with a single species first. Yeah. So homonuclear. Yeah. And actually, so how do we create atom pairs with a homonuclear system? And that turns out to be rather easy. You actually take your BEC and turn it into an insulating state when you go to the superfluid to insulating transition. And I have no details on this transition here, and I think our colleagues, Emanuel Bloch and others, will talk about this a bit in this lecture. So I actually decided to skip this. Just for you to remember, what we use this as a tool. Yeah, so we use it as a tool to prepare the so-called two-atom mod shell with a quite high probability. So the center part of our trap, typically it's 50,000 particles that are actually at doubly occupied sites. So to give you numbers, I haven't written down any numbers here. We have a BEC of 100,000 atoms. We are able to turn 50,000 of these into pairs. That's the limit that you get, basically the limit that you get from harmonic trapping. If you had box trapping, this would be different, would be higher. So the two-atom mod shell contains 50,000 atoms. That means we have 25,000 molecules at maximum. Yeah, and when we do it in this way, and I will not tell you, you can do it in another way and even more efficiently. But with the two-atom mod shell, we get about, well, for sure 20,000 molecules. Yeah, in the lattice. These we then turn into the weakly bound molecules. Also here, I won't show you exactly the details how we do this. I showed you the schematics, but not the specific states. And then this ground state transfer efficiency is, in this particular case, for homonuclear cesium is 80%. Not 90%, but 80%. Why is it 80%? Because it turns out it is a 4-photon process. Homonuclear cesium is not the way the molecular potentials overlap, bottom and top. It turns out that a single 2-photon stirrup step will not work. At least we played around with this, no chance, but we need a 4-photon stirrup. So we actually set up 4 lasers that were all phase coherent to go all the way to the ground state. And this is the schematic, so it's not a 3-level system, it's a 5-level system from the initial state, which is basically from, if you count from below, it's the 155th vibrational state all the way to the ground state, yeah. And this is the scheme of doing transfer 1 step, 2 step, back and back, yeah. As this is generalization of what I just showed you. So I see again for questions in the chat. Yeah. So okay. Yeah. So NACS is done in a single atom tweezer trap. Yeah. So the Harvard experiments, yeah, are done with single molecules in tweezers. That's certainly a different situation because, well, in the end, we are interested in really in the many-body system. With tweezers, you can perhaps eventually take it into a many-body regime, yeah, but that still has to be demonstrated. Okay, so that was this question. So this shows the transfer from the initial state to the ground state for homonuclear cesium. This shows the intermediate transfer step here with an efficiency of more than 75%. When optimizing everything, we were actually able to demonstrate an efficiency of 80%. And this is while all other lasers are in resonance, the 4th laser is being detuned, and this is the efficiency. Yeah, so about 80%. So each step being about 90%. So there are and I actually indicated that earlier here, there are some defects, yeah? So this red molecule here is a molecule in the wrong state or actually something that got lost on the way, yeah? So it's actually not totally clear where this molecule is lost, into what it is lost. We don't know, yeah? One can make guesses. So 80%, but that's actually quite a dense sample, yeah? 80% at very low temperatures. And talking about temperatures, this is an image of a band mapping image with where we exaggerate the color scale, and this shows the lowest Brion zone of our lattice, and you see that essentially all the molecules are in the lowest band. So we don't excite the molecules to higher states in the trap, in the band, and so in the lattice. Yeah, so that's actually quite important to know, and it could have been different. Yeah, because I haven't said that. You want the initial state to be trapped and also the final state to be trapped. It turns out we have fortuitous at the trapping wavelengths that we are using. The initial trapping and the final trapping are almost identical, just by accident. Yeah. When I talked to the funding agencies, I said, well, I computed it and I knew that it would work, but actually, admittedly, it was an accident, and we're lucky. And it turns out, also for KRB and some other molecules, we are near this sort of magic wavelength where trapping in the initial state and the final state is almost identical. And we, if it were not, you would actually do motional excitation of the molecules, yeah, in the lattice. Okay. Talking about lifetime, yeah, this is an image of a long time ago of molecules trapped in the lattice in the lowest band. The lattice is at 1064. It's rather far detuned from the relevant excited states. The lifetime is 8 seconds. Yeah, so that's actually long for anything we ever want to do, and I'm sure it could be optimized. But it shows that these molecules, when they are left alone, sitting at the individual wells of the lattice, not doing anything. Yeah. Now, I'm showing you actually this to show you now what happens if you let the molecules interact. Yeah. So this brings me to the question of stability. Yeah. So collisions, two-body collisions, or perhaps effective three-body collisions. And this now shows data where we release the molecules, as indicated here, into stack of pancake traps. Yeah, so we have the molecules in this vertical lattice. At the end, after we remove the lattice beams from the horizontal directions, and the molecules live in traps that are 2D. Yeah, so they collide in 2D. And what we see is that we have now a lifetime. If you fit a 1/e, but it doesn't fit at all, it's actually that lifetime is on the order of 10 milliseconds. So before it was almost 10 seconds, now it's 10 milliseconds. So letting the molecules collide decreases the lifetime by 3 orders of magnitude. Yeah. So what I'm showing you here, this is the molecule number as a function of hold time. Now it's not seconds, but milliseconds. This is logarithmic. And the gray dots are data, our molecules in the trap. So initially we have about 20,000 molecules. And then after 80 milliseconds, we have 2,000 molecules left over. And the lines that I'm showing are fits, yeah, and some theory. So actually the red line is a two-body fit, actually for the entire range. Doesn't work. Yeah, it doesn't fit. And I have to say, certainly we require the two-body fit to agree with our initial data. Yeah, that's a constraint you can easily do. And so you see, it doesn't work. Two-body fit doesn't work. It works initially quite well, but it doesn't work over the entire range, over these 80 milliseconds. We can do a two-body fit on the first 10 milliseconds, then it works even better in the first 10 milliseconds. Certainly it doesn't work as well back here. But this tells us it's a two-body process initially, yeah. And the dash color lines actually assume that we have something complicated going on that I will explain to you in a second, namely the formation of complexes. Yeah, with some one free parameter. I will show you that in a second. Sort of free parameter. Yeah. So the upshot of all this is what we measured is that the initial decay is two-body. It's not one-body and it's not three-body. Yeah. So it's molecular two-body collisions. Yeah. Quite interesting. So what's happening? And this is summarized here. This is what John Bone proposed nearly 10 years ago. That if you have two molecules colliding, they can actually form a complex. Yeah, even though we have them in the very lowest state, they cannot relax in any way. They cannot form a trimer. They cannot form a 4-atom molecule. Yeah, but transiently they can go into this 4-atom state, and they can break up again into this into these initial dimers. But what they can also, if the lifetime of this complex is long enough, it actually can collide in a 3-body type with another molecule, and that can lead to loss from the trap. So the formation is 2-body, but the loss is 3-body. So this turns actually into a difficult experiment, and the rate equations on the next slide. First, we have three parameters: the complex formation rate, the dimer complex fission rate, and the lifetime of this molecule that breaks up again into these complexes. And that's actually the model here for the number of molecules and for the number of complexes, where, let me walk you through this, where you have a rate of complex formation, where you have a rate of complex breakup, and where you have a rate of complex relaxation with another molecule. That's the only thing that's around, a molecule. Yeah, it's a pure sample of molecules. Yeah, that's the rate for, that's the number for the molecules, and that's the number of complexes in the same way. Yeah, so that's a simple model, not assuming any temperature dependence and so on. This is in effect done in the 0 temperature limits anyways. Yeah, so temperature effects will probably not play a role, that's the simplest model you can set up. Yeah, and now what you can do is you can see we can measure alpha. Yeah, that's what I just showed you. Yeah, alpha we can fix from these measurements immediately, because that's the initial decay. What we don't know is these other two parameters, gamma and kappa. Yeah, so we can do those something. Our molecular friends tell us that they actually know kappa. They can actually calculate universal kappa from van der Waals theory. So they can actually give us a number here, and when we fix that, we can get that gamma, yeah, or 1 over the lifetime. So gamma is this lifetime of this molecule complex. yeah, tau. And this is actually shown here in this plot. This is again the data, and I'm plotting now the curves that all fit our data for 3 possibilities of this kappa, where we have a universal kappa from van der Waals theory. I'm not detailing it at all here. We have 10% of that, or we have 10 times that value. And choosing that, we can get the dash curves here are number of complexes that we then have in the system, yeah, and that actually is sizable, yeah, in particular for this value, yeah. Anyways, this fits the data very long. Now with these 3 numbers, you can get these lifetimes, and you see the lifetimes. Even that lifetime here, 4 milliseconds, is very, very long. So these molecules come together and stick together for 4 milliseconds, and this here is actually infinite, yeah, 300 milliseconds, I would say, for a collisional process, yeah. So that's actually quite amazing, and and then the question is, what's happening there, yeah? So our data is consistent with this model, but I have to tell you, long story, we've never published this. This is a nice data where we decided never to publish it because we were not sure whether there's something else. Yeah, okay, we could publish and say, well, that's what we see. But I'm a person who always wants to understand everything. Perhaps one shouldn't have that attitude. So in particular, there's now a discussion in the literature whether there's photochemistry going on while these collisions happen. And there's some data that supports that claim and some data that does not support that claim. Anyways, yeah, so I close this chapter and I come back to rubidium cesium. Okay, I see a question in the chat.
Yes.
Let me see. Open it. Why does it not open? Chat, it opens.
So maybe I can read it. So is interaction among the molecules in the lattice affect the stability?
So, in the lattice, when they are actually not allowed to collide because the lattice is too deep, yeah, then nothing happens, yeah. So the molecules live very long. So we don't think this interactions play a role when we actually have the lattice on. But when we allow them to move in 2D or in 1D, I haven't shown that. We've done also experiments in 1D, and one can but then the analysis gets a bit more complicated because in 1D hell breaks loose because of the confinement, yeah. So anyways, but we have a lot of on that, and but we see also we see very strong loss immediately, and it has to be due to interactions. Yeah, unfortunately for the molecules, we cannot turn off interactions by some other mean. We can only turn off interactions by adding potentials. Yeah. Okay, now let me come back. So how am I doing in time? I have to watch a little bit time. I started
about 30 minutes. You started at 15 plus 4, so you have around 30 minutes or so.
30 minutes or so. Okay, then I'm doing fine time, I think, yeah. So let me go back to rubidium cesium, yeah, where we want to create these atom pairs initially, yeah. And this mod insulator with 2 different atoms of each type at each site. Yeah, and then go through this route as I indicated earlier. Yeah, so this we discussed now, Fetchback association, the stirrup transfer we discussed, and it can be done better, but I think it's very well understood or good enough for practical purposes. And then this initial step. Yeah, and in fact, the Giller group 5 years ago published a paper on mixing a mod insulator and a band insulator, and in our case, we find that this is, in fact, the bottleneck. So perhaps with fermions, it's a bit easier, yeah, because as I mentioned earlier, so this is the bottleneck. So creating atom pairs is the difficulty. And so let me take you to the next comic. So the idea is to start with a single atom mod insulator state. Yeah, so this we know to do how to do very well in our lab. In one of our machines, we do this essentially every day, and we can localize 90% of the cesium atoms from the BEC in this way. Yeah, so this superfluid turns into almost perfectly into this one atom mod shell, and actually cannot turn 100% into that because you have the superfluid fringes outside. Yeah, so we are close to the maximum here. And then the idea is to bring in the rubidium BEC from the side. Yeah, initially separated actually, as I will show you in a second. Yeah, and then to bring in the rubidium in some way and to raise the lattice further and to go through the phase transition to localize rubidium one more time, as indicated here, yeah? So what we want to do is we want to allow one rubidium atom into these sites, but not a second one, yeah, because that's detrimental, yeah. So that leads to three-body loss, and in view of Efimov states and strong three-body collisions, we don't want that, yeah. So this process should not happen. But the question is, how does the first rubidium enter on the site where you already have a cesium atom? So if you think about this, we need to do something about it. It doesn't do this on its own, yeah. And we want to prevent the second rubidium atom to come in. First of all, you need interaction control for that, yeah. And the tool is now an interspecies Fetchback resonance between rubidium and cesium. So this is the situation, again, of Fetchback resonances. I think I can flash this quickly. The generic picture of a zero crossing in the vicinity of a Fetchback resonance here, yeah. And then we want to populate this bound state on the resonance. So what we need is actually, we need both. We need the zero crossing and the bound state that pops up at threshold. Yeah, so that's what will be making use of. And explicitly say this is important for us, the zero crossing. So this is now the real situation. This is the theory result from a lot of measurements that we did long time ago. And we got a lot of support here from, in particular, Svetlana Kotochigova from Temple University to identify all the resonances and the bound states as indicated here. So this is the zoo of bound states. Well, it looks bad, but it's not so bad. It's all, you see the magnetic field. We control our magnetic field at the level of milligauss, and so we can address each of these resonances certainly individually. The resonance of our choice is the broadest one here at around 350 Gauss. I'm zooming in. This particular one here, that's the one, and the bound states below. Yeah, these are the ones of our interest. Yeah, so near this resonance, we have also the zero crossing. Yeah, I'll zoom in a second, and the slope at that zero crossing. Yeah, and let me go back. What's also important for an experiment is how gentle the slope is. Yeah, it should not be too steep, because if you have magnetic field fluctuations in the lab, which you can never avoid, you will wiggle around too much here. So the zero crossing is sufficiently gentle, so it's usable. Yeah, it has this slope of 3 Bohr radii per 10 milligauss, and that's reasonable. So having said that, what about the other interactions? Yeah, so we have now, this is rubidium cesium. This shows the scattering length of rubidium cesium in specific spin states. I haven't detailed that, but it's the very ground states, hyperfine ground states for both of them. What about rubidium and cesium? Yeah, there are 3 parameters, but only 1 knob to turn. Yeah, just remember that. We have only 1 magnetic field, and it's difficult to do anything else. Yeah, so rubidium is not a problem. It has 100 Bohr radii and also almost no loss. Yeah, so rubidium is easy cheesy. Cesium is potentially the problem. And if I go back to that value, 350 Gauss, that's actually where cesium has, and I showed you this picture earlier, or similar one, where the scattering length is on the order of 2000 Bohr radii. Yeah, so this shows the scattering length for cesium, the lowest hyperfine state specifically of cesium as a function of a magnetic field. You see these 3 wonderful resonances. In fact, this resonance here at 800 Gauss is the widest resonance in the field as far as we know. Yeah, the widest Fetchback resonance. And but we sit here at on this slope here at 350 Gauss. So cesium scattering is very strong, and at 2000 radii positive, but you still expect the 3-body loss rates to be very large. So without showing you details, I'm just showing you the data. This is the lifetime of cesium atoms in a mod insulator state. So in a state like this, yeah. Sorry, something popped up. So in a state like this, the top one here, yeah, 1 atom per site, yeah. And the lifetime as a function of lattice depth. Yeah, so actually we go through the phase transition around 16 recoil depths. So this is a typical unit for the depth of the lattice. If you're not familiar with this, don't mind. This is the horizontal scale is just depth of the lattice. Here is the phase transition, and we are deep in the insulating regime. The lifetime is not 10 seconds, it's 2 seconds. Yeah, okay. We don't know why. it's finite, yeah, but it's actually good enough for all practical purposes. And it's actually our it's ongoing work to understand what's going on there. If you go away from that lattice step, you will get very short lifetimes. Yeah, here hundreds of milliseconds or even below 100 milliseconds. Yeah. So the preparation is certainly, we do the preparation for the sample at low fields. Yeah, actually we prepare the sample around 20 Gauss down here, and then we ramp the field to 350 Gauss. Okay, so that's finite, but okay, yeah. So how do we do the experiment now? We have a lattice setting with two samples, rubidium and cesium, and let me even simplify that setting here. Just we have 60 laser beams going into this chamber for everything, for molecular control, imaging, laser cooling, advanced laser cooling, additional laser cooling, and so on. So I'm totally simplifying it now to only the lasers that we are using for the trapping and for the lattice on top. So the lattice is actually very big. It almost doesn't do any trapping. It's indicated here by these pancakes, top and bottom, left and right, a cubic lattice. So let me even simplify that. So we have these two superfluids. We turn the right one, cesium, into this mod insulator state, and then move our superfluid rubidium on top of cesium. I have to say something about that. And then we create this, or attempt to create this double mod insulator state. So what does that need? It needs two things. It needs superfluid transport. So to give you a feeling, this goes across about 100 microns, so 200 lattice sites, because each lattice site is half a micron away roughly. That's one thing, the superfluid transport. And what we need is interaction control as when the two samples meet. Yeah, and that is now shown in a moment in this data. But let me just tell you quickly how we detect. Yeah, well, detection, you know, we go back to atoms and we detect atoms separately from molecule for cesium and rubidium via this Fetchback trick. Yeah. So this is now the specific molecular level scheme. So this shows binding energy of the most weakly bound states as a function of magnetic field around this resonance region that I just talked about. Here is the entrance door that I've talked about, where we take the atom pairs into a very weakly bound molecule, this state below threshold, and then the state actually on an avoided crossing turns over. So there are some states that I have not labeled. Actually, I have not labeled any of the states because it's not relevant here. And only one state I should highlight, there's a very weakly coupled state here near the resonance. Yeah, the resonance is actually caused by this avoided crossing here below threshold, pushing this green line through threshold. That's the relevant state. And there's another weakly coupled state. It turns out this is sufficiently weakly coupled that it doesn't hurt us, but it's there. Yeah. So that's the route from atom pair to molecule with a binding energy of a few megahertz in the end. And this is now how the experiment works. Yeah, we move here. We show the overlap of the two samples, and we show how efficiently we produce these Fetchback molecules. Yeah. So on the left, it's absolute numbers. On the right, it's normalized to the number of the atoms in the cesium BEC. And since we know we turn 90% of the cesium BEC into lattice sites, this gives us approximately an estimate for the filling, for the fractional filling, actually a lower bound, in fact. Yeah. So this is as a horizontal lattice position. Yeah. So you see we have sort of a top hat overlap because we have these two samples that then merge, and then when we go beyond that, we actually, the overlap is not as good anymore, spatial overlap, and you see what the size is. Yeah, so we have to control this at the level of micrometers. This is horizontal overlap, and this is vertical overlap. So we have to make sure we really bring these samples on top of each other at the level of a micron. And this is now crucial. This only works. So we optimize the spatial overlap, but it only works well if we null the interspecies interaction, the rubidium cesium scattering length. And this shows the same data now as a function of interaction strength, number of molecules on the left, lattice filling fraction on the right, as a function, or lower bound for that, yeah, it's slightly higher probably, as a function of the interaction strength. And we see that we can, we obtain a maximum here at the value that's consistent with 0, yeah, within our error bounds. Okay, so this is how we do this, yeah. So we have about 5,000 to 6,000 of these molecules when we overlap the two samples in the lattice, and the lattice filling fraction at the center of this trap is on the order of 30%, perhaps a bit better, but it's not unity yet, yeah. So what is the main enemy, yeah? What is the main enemy? In fact, let me go back quickly to that. It's when we overlap the two samples, when we actually, let me see this plot here, yeah. So when we bring in the superfluid rubidium, the superfluid rubidium is superfluid, yeah. It's not yet localized. Certainly we don't want it to localize initially. And there's a certain probability, Poissonian probability, that we have not just one rubidium atom at a site, but 2, yeah, or 3 even, yeah. So that's non-zero. So we have a certain probability that that we bring in more than one rubidium atom, yeah. That's one enemy or one problem, yeah. It actually turns out that the lifetime of the cesium mod insulator already is a problem. As I said earlier, it works, but it works only so-so. So we see that while we bring rubidium on top of cesium, while we do the dynamical process, we already lose cesium. Cesium hasn't seen rubidium yet, but it's still, we already lose it, yeah. So that's also one problem, yeah. So that this lifetime is not finite, yeah. And then we do this overlap, and I don't show you data for this, yeah. I actually didn't bring it, yeah. The question is, when I go to this comic, how quick can you do this, what I've called superfluid transport, yeah. So this blue arrow here, so you have a superfluid here, and how quickly can you move this? And there's actually a speed limit. And we see the speed limit, yeah. We actually have to be significantly below the speed limit, because it turns out if the sample is not superfluid anymore, when we go over here, we don't create any molecules. So it turns out the fraction of molecules is directly related to how what the BEC fraction of that rubidium BEC is. So it's strongly related to that. So we have to watch it. So as we move the sample from left to right, we have to make sure that it stays a superfluid. And in fact, we were not sure whether this would work at all, because I'm not aware of anybody in the literature moving any superfluid through a lattice across 200 lattice sites. Yeah, so this is actually brutal. We have so what we do is we move the underlying dipole trap, as indicated here, and move it just across. Yeah, and so you see everything warps as you do this, and it could break loose. It turns out it works pretty well. Yeah, but the details of that have to be still sorted out. So actually, we have not identified a single reason, but it's, I think, a multiple of reasons that can be optimized. Yeah. Okay, so then perhaps I stay with this comic because I haven't brought any other picture for that. You could do this in a different way. You could actually merge two samples, Rubidium Cesium, that are not initially side by side. Here they are next to each other, yeah, really horizontally at the same level, and we just move them we move the rubidium sample from left to right. You could actually move them up and down with sort of pancake traps. So you have two samples that are 2D at the outset already, and then you just merge, do this merging along the tightly confining direction, along the pancake direction, the tightly confining direction in a pancake. So in this, if you were to do this, so you prepared cesium in a 2D situation, rubidium in a 2D situation, and in fact, we'll see that later, our quantum gas people, quantum gas microscope people know to do this really well. Just one layer of rubidium atoms, let's say, and then to merge that one layer in 2D layer with the 2D cesium layer. And then actually the merging would be only two-body, and not, you would not have the problem of any three-body processes. Yeah. So you would, in this sense, not move a superfluid through the lattice, but you just would move two mod insulators on top of each other by removing a barrier in between. Yeah, I think those of you who know a bit about lattice physics can immediately visualize how that can be done. Yeah, so that's actually the goal of all these endeavors at some point, because for a lot of these experiments, we are totally happy with two-dimensional dipolar molecular samples. Okay, so let me see.
There is one question. Would you like to take now?
Yeah, I can take questions. I'm actually almost at the end. I think I've rushed a little bit. Yeah. I'll take questions in a second. Let me just summarize perhaps this part. Yeah.
Okay.
So this rubidium transfer, this two-photon process, is very efficient. The lattice filling is decent. Yeah, it's not yet where we want to be, but it's decent. The efficiency for cesium homonuclear is also decent. I think it can be pushed, and we actually know what our lasers need to have more phase coherence. Yeah, that we know. This sentence here is a little bit at the moment perhaps challenged by the results that I'm citing down here. I think we used to have the coldest molecular samples in Innsbruck, but I think the GILAD people have beaten us now. Yeah, but I left the sentence because a little provocative. Yeah, rubidium KRB is doing really well, as you will hear from Junyi. He can take his gas of KRB molecules into Fermi degeneracy. Yeah, at temperatures significantly below a microkelvin. I forgot what exactly his Fermi temperature is, but it's on the order of 100 nanokelvin. So, and you, well, stay tuned. This is a really nice result from last year. And in fact, certainly in Innsbruck, we want to do the same with our bosonic systems for rubidium cesium and for potassium cesium in a similar way, but well, similar meaning into a similar regime, but with the techniques that I've discussed so far. Okay, let me take questions at this point. I open the chat.
So shall I read it?
Okay, I can read it. And the first question is: are we able to handle each atom in the two-atom site, or is it considered as a molecule and handled together? So yeah, so perhaps just initially we localize two atoms at a lattice site, and then we turn that atom into that atom pair into a molecule. So certainly the question is when there's an atom pair and when there's a molecule, what trap frequency, for example, do they see? Is there any excitation as you go from the two-atom state into a molecular state? And it turns out no, because the atoms, they have the molecules have twice the mass, but they also have twice the polarizability, the AC polarizability. So we don't see any excitations as we go from the two-atom state to the molecular state in the lattice. So the next question is, can it possible to have two atoms superfluid in one place? Yeah, that's what we actually, I think the question aims at what we did with cesium. Yeah, let me actually go back quickly. So with cesium, I'm going in the wrong direction. With cesium in this picture here, my comic, yeah, we work just on homonuclear cesium. Actually, we have initially a superfluid of cesium, where the chemical potential is such that we will actually preferentially fill the two-atom mod shell as we raise the lattice. Yeah, so this is so basically what we do with the underlying dipole trap, weak dipole trap, we set the density such that we fill up the two-atom shell maximally, but not the three-atom shell. Yeah, and then it turns out that about 50% of the atoms sit in the 2-atom mod shell and 50% sit in the 1-atom mod shell. Actually, my comic here is not quite correct because it should be 50-50. Yeah, so, but the center part is a superfluid with sufficiently high density that you create atom pairs in the lattice. Okay, so that's one question. Perhaps I answered that. Yeah, but I'm happy to take further questions. So next question, let me see.
What aspects of Fetchback
association helps to improve the phase-space density as compared to photo association? Well, Fetchback association, in particular when you do it in a lattice, is actually very efficient. Yeah, so doing this step from here to here is 90% efficient. Yeah. So and we what we actually do when we create from the atom pair, we create the molecule, we already reduce the internuclear distance by a lot. And in fact, it turns out, I didn't show that and I didn't bring any slides. When you go via avoided crossings to even further more deeply bound states, you even reduce the internuclear distance even more. So these molecules are already fairly tightly bound. I mean, they're still van der Waals molecules, and they have a much better Frank-Condon overlap with the excited states that you need for the stirrup transfer. So that for sure helps a lot, yeah. And in fact, as I said earlier, we found this by accident, yeah. We found that our Fetchback molecules are susceptible to multi-frequency light, and they were not susceptible to single-frequency light. And that, so we saw that the Fetchback molecule, we can much more easily drive optical transition on the Fetchback molecules. So I think this was this question. Let me see the next question.
Could you elaborate more about experimental
method of merging two 2D lattices along the tightly confining direction? Yeah, I think for this, I mean, it hasn't been demonstrated certainly, but I think what we do is we prepare separately two-dimensional condensates with the way how you do it is you start with your 3D condensate, but then you load into light sheet traps, so traps that you generate by focusing a beam very tightly along this horizontal direction. So the focus is along the vertical direction, so that it's a horizontal light sheet, and then you load your initial 3D condensate adiabatically into this 2D plane. That I think we know how to do. The community for sure knows how to do it. And you have to do this though for 2 samples, yeah? Top and bottom, rubidium and cesium. And I think that can be done. I don't see any problems with this. And then certainly you have to overlap everything with the lattice. And then you have to keep in mind, you have to have a lattice also in the vertical direction and take away the barrier between the 2 samples. And that also in principle has been demonstrated by actually doing this in a super lattice type fashion, where you have 2 different frequencies in the lattice, where you have a barrier in first, and then you remove the barrier by removing the higher frequency components in your super lattice. That in principle can also be done. But as far as I know, it's not been demonstrated, yeah. But we are working hard on this, yeah. So to do this with Rubidium Cesium, and in particular with KCS. But we'll see. I mean, we have to marry all this, combine all this with electrical field control plus high resolution imaging. So in fact, we are working right now on designing a chamber where we have everything, yeah. Lots of beams coming in, electrical field control, Faraday caging to avoid fields from charging up lenses or vacuum components, windows also. In fact, Jun Yi will tell you how they do it, and we are working on something similar, but with hopefully with a bit better resolution. What he has in his chamber, he has 2 plates, transparent plates, but they are coated so that they are electrically conductive. And so he can put voltages on these transparent electrodes. It's Indian tin oxide, ITO it's called. And these ITO coated glass plates are the top and bottom electrodes, apart from other electrodes that he has in the chamber. And that has to be all combined with the short working distance of your lens for imaging, plus the capability to create very deep lattices for imaging purposes. If you want to image individual atoms later on, so you do all the entire procedure, and then you want to image these atoms individually, then you need to raise your lattice by a factor of 100 or perhaps even a factor of 1,000. I think 100 is okay with proper laser cooling, and then image. And so you need to also be able to have high light powers inside your chamber while you then image. Yeah. So I think that perhaps answered that question to some extent. Yeah.
There's one more question.
So there's once having 2 atoms per side. What is further trying to do with these lattices? So I mean, the application of 2 atoms per side, our primary application is turning these 2 atoms in the lattice into a molecule. Yeah, so the goal is really to make these molecules. I hope I understand your question right. When we have other endeavors in our group, in fact, there's a publication from late last year that we finalized after many years of work on not molecules in the lattice, but doublons, atom pairs, move through the lattice together, even though they are not bound as a molecule. You can do this with atom pairs that interact repulsively or attractively, and we call them doublons. And we actually, it turns out the theory has a hard time modeling our system. Yeah, we have very good control by now, and it's hard to model the processes that actually happen. So the goal of these 2 atom doublon systems is to create novel superfluids. There are proposals in the literature to create novel types of superfluids with atom pairs in lattices, bosonic atom pairs actually, not fermions. Yeah, bosonic atom pairs, and well, actually at the moment we are not doing this because of lack of time and manpower and human power. But it's an interesting avenue on its own. Yeah. I don't have any slides on that, unfortunately, to detail more on that. Yeah. Okay, and certainly I invite everybody, just send me an email, just write, I was a member of the school, and I will immediately answer you any questions that you might send me via email. Yeah, I'm very happy to do so. So let me actually then, actually with these questions, I'm actually really well in time. Let me show you the last slide of my lecture. There's another question. Can there be atom interaction in quantum walk? Well, certainly, yes. That's actually a very interesting question, yeah. If you have quantum walks in these potentials, we have interactions, and that actually modifies quantum walks drastically. Yeah. Actually, we even have some data from a long time ago, some years ago, looking at similar things in lattices. Yeah, but that's a separate story. Okay, let me go to the end again. I don't want to exit my. So the summary I've just told you already, yeah, and this is should acknowledge my group. Yeah, this picture is actually heavily outdated because it was taken a year before Corona, almost a year before Corona, and since then we have never come together again. Yeah, so unfortunately, yeah. So we haven't taken a group picture. Yeah, we need to do this. Hopefully in a few weeks we can do this. But let me acknowledge the people. There's Deborah Capecci and Camilo Cantillano, who are actually now the students trying to improve this system, this Rubidium Cesium system, yeah, that I've been talking about. And to take it to the next level. Yeah, so we've been, I have to say, the data that I showed you is a few years old, so we have been rebuilding since then. Yeah, you saw I mentioned that we have 60 laser beams entering the chamber. These 60 laser beams come from about 20 lasers, most of them diode lasers, and we decided this is too complicated. We need to simplify. So we actually bought a few commercial lasers, and we reduced the number from 20 to 12 or so. Yeah, it's not 5, it's 12 still, but it reduced complexity, but we are not back yet, admittedly. Yeah. So these two guys are working on it, and in fact, we've just been able to get a young postdoc from India. She's not with us yet because she's in home office in India. She cannot travel. Supervising is done by Manuele Landini, the senior scientist, and I also want to acknowledge Boda Santra, who was with us until 1.5 years ago, roughly, if I remember right, and until the end of 2019, and actually worked on a different project. Yeah, so Boda worked on the single species atom experiment. We actually by now it looks like that we have also some very nice results, but the newest data is not yet published. Okay, so this brings me to the end of my lecture on molecules. And again, I should do an advertisement for my friend and colleague Jun Yi, who will be talking, I believe, tomorrow. Also, Martin Zwierlein, also a friend of mine, will be talking. I'm very honored to be here in this group of friends. Stefan, also a good friend of mine. Didi Leibfried was a postdoc when I was a PhD student. Christian Roos, actually, I grew up with when we were kids. So a small community, yeah. Tilman Esslinger, Immanuel Bloch. So it's a nice community, good friends of mine. And I really wish you a good time with all the other speakers. And you will see some fantastic results over the course of the next few days and the next 2 weeks. Yeah, I'm very confident. Okay, any questions?
Yeah. So first of all, Christoph, thanks a lot for this very nice talk, yesterday's and today's, and also for showing very basic equations. I hope many young students would learn a lot from those things. And is there any questions?
Talking about young students, yeah. I cannot prevent of doing this little advertisement here. Wait a second. We still have open positions. At the moment, we have good funding. Yeah, who knows how this looks in 3 years from now? But at the moment, we have good funding, and we are still looking for one postdoc at the moment, and very hardworking and smart PhD students. Yeah, but yeah. Anyways.
Hey, can I ask a question, Bodhayitya?
Yes, here, please go ahead.
Okay, so fantastic talk, and it's amazing to see how many lasers you have and what are the things you can do and the amount of control you have with all the lattices and all. So what is how is this potassium cesium going to be different from rubidium cesium? So, I mean,
yeah, good question. Yeah, so actually potassium cesium was started with the goal to do the fermionic situation. Yeah, so to be directly competitive with Gilla people. Yeah. And it actually, our source is such that we have a enriched source, and we can easily, in principle at least, easily switch to potassium. But I think at the moment we're not doing this because actually the leading student is this gentleman here, is Govind Unikrishnan. You easily recognize that he's from India, and he's the most senior student right now on this project. And we decided at the moment to enter into this race of making a Bose-Einstein condensate of molecules. Yeah, so we at the moment will stick to KCS as a boson, and we have a little internal competition also, if you wish. Yeah, friendly internal competition. And I mean, rubidium cesium has the advantage that it has all components in principle working, but the electrical field control is not as good because it's still our old chamber where the electrodes are outside and not inside, and we have not rebuilt the chamber yet. That's different in KCS. KCS still needs to do some spectroscopy, and we still have to identify the excited state for our ground state transfer. But there we have a better chamber right now already with inside electrodes. And the next generation's chamber that we're working on right now, actually we already have a next generation chamber, but it turns out it's a glass cell with special coatings, everything, lens inside with high resolution, but it turns out we have a vacuum problem. And it's not a leak. It's an outgassing problem. That's the only reason that we can say. So we, unfortunately, we have to give up that chamber, and we will flange on a new chamber next generation where and the outgassing problem with the commercial cell, we don't have that under control, unfortunately. Yeah. So actually we've seen, actually Govind has seen, it's not too long ago, a few months ago, that we were able to transport ultra-cold potassium into that chamber. And when the transport worked, it turned out the lifetime in this chamber was just 2 seconds. And in the collection chamber, where we can actually also make BECs and have electrodes, we have a lifetime of 20 seconds or so. So of our cold samples. Yeah. So the lifetime gets reduced by a factor of 10, and it's evidently a vacuum problem. So we are working on this. But anyways, there is this race, I would say, yeah. Whoever's going to win it, who makes the first Bose-Einstein condensate of molecules.
So fundamentally, do you see any problem with getting a BEC of molecules? I mean, which are not, so these are composite bosons. So do you see anything different from atoms, which are sort of, we are used to
well, the
identical
fundamentally what's different is the collisions, right? And it's so it will most likely only work in 2D. Yeah, so we have to categorize the molecules. I hope you can see me in this way here, perpendicular to the plane. In fact, the nice surprise you will hear from June tomorrow. The system is also surprising its fermions, and that has nothing to do whether with being fermions or bosons, I think. Yeah, are also surprisingly stable in 3D. Yeah, so he actually they also thought it's only going to work in 2D, but they find, well, you do 2D and then you try to go to 3D, and it seems to work also. That's a surprise, yeah, because it's been discussed for 10 years now that that this might not work, yeah. Even it was discussed that even the 2D case is not going to work, yeah. So it's not. I'm not totally sure whether it's working, but I've been optimistic that we will see a Bose-Einstein condensate of molecules within the next 2 years.
Oh, great, very nice.
Of ground state molecules, yeah. Not we know, you know, there are weakly bound molecules, Fetchback molecules, fermions, BC, S crossover. That's all been done, yeah. But these are not molecules. Let's be honest, it's atom pairs, yeah. Extremely weakly bound atom pairs, yeah. No, I'm talking about chemically bound molecules. And yeah, within the next 2 years, I'm pretty confident that one of the groups that I've listed, or perhaps some other group that's not on my horizon, will do it. Yeah.
Great. Okay, thank you very much.
Yeah, and then we are in with dipolar superfluids that are really strongly interacting. Yeah, so that will open a new door. Yeah.
Yes.
That's my claim. Yeah, I'm optimistic, but my optimism always was justified in the end. I see for almost everything. Yeah.
Good. Okay. So I don't think there are any other questions, right?
No, there's no question.
Okay, then thank you once again, Professor Nägerl, for this wonderful set of lectures. And I think hopefully we'll have you sometimes here in person.
Yeah, thanks a lot. Yeah, thanks a lot for having me. Yeah.
Yes, thank you.
Yeah, I'll see you around during the school. I will for sure also listen to some of these talks. Yeah, I mean, some of the things I've recently and also talked to discuss with these colleagues. But yeah, very nice program.
Thank you. Yes, thank you.
Okay.
Okay then.
Thank you.
So
okay. Thank you very much. Yeah. See you around. Bye bye.
See you. Bye.
Bye.
So we come back again in the evening at 8 o'clock for the next talk by Dietrich Leibfried again on trapped ions.